Why is there something rather than nothing? How did everything begin? What was there before the beginning? Where did the material come from that created the Big Bang? What happened in the first instance to create that material? Why are we here? When it comes to understanding the universe, trust me, we've barely scratched the surface. These questions I asked above have been circulating in the realms of human curiosity for countless generations, transcending time and spanning cultures. We've been sending different telescopes, like the James Webb and Hubble, to explore the depths of the cosmos. These marvels of engineering have actually done a great job in unraveling some of the universe's secrets, possibly shedding light on a small fraction of its vastness. Day in and day out, we've diligently scanned the skies, capturing breathtaking images of distant galaxies, nebulae, and celestial phenomena, expanding our knowledge of the cosmos with each observation. Through these telescopes, we've witnessed the birth and death of stars, marveled at the intricate dance of galaxies and cosmic collisions, and unraveled the mysteries of black holes. We've measured the redshift of distant galaxies, allowing us to peer back billions of years into the past, offering a glimpse of the universe in its infancy. But with all of these magnificent discoveries, we still have numerous unanswered questions everywhere. Why? When? How? Where? Can we ever answer these questions? Well, you have to keep watching. The last star will slowly cool and fade away. With its passing, the universe will become once more a void, without light or life or meaning. This statement was mentioned by physicist Brian Cox in a BBC series, "This is how everything might end." Some other theories suggest that our very own Big Bang, the genesis of our universe, might have originated from a previous incarnation of emptiness, a cold, dark, and empty universe similar to the one awaiting us in the distant future. This is just the first theory. What about theory 2, which suggests there is no first man or woman, no singular event that sparked the universe into existence? Instead, the universe has always been and will always be existing in a state of perpetual existence. According to this theory, the cosmos undergoes an unending series of expansions and contractions, with each cycle seamlessly transitioning into the next. It is an eternal cosmic dance, where the fabric of reality remains constant, unaffected by the passage of time. This theory challenges our conventional notions of a linear timeline and a definitive origin. It suggests that the concept of before and after loses its meaning, as the universe persists in a state of unending existence. It invites us to reimagine the nature of reality itself, where the eternal cosmos encompasses all possibilities. And then, Theory 3 takes us even further, suggesting the existence of infinite universes, each with its own set of physical laws, constants, and conditions. According to this theory, our universe is just one among an infinite ensemble of parallel universes. Each universe within this vast ensemble may have different properties, leading to a staggering array of diverse realities. Every conceivable outcome and configuration exists, encompassing an unimaginable breadth of cosmic landscapes. From universes where the laws of physics are entirely different to those where life takes on forms we can scarcely imagine. Strange, right? The next one, Theory 4, suggests that the reality we perceive as the universe is, in fact, a sophisticated program created by an advanced civilization or a higher intelligence. In this scenario, our entire existence, including the laws of physics, the fundamental particles, and even our own consciousness, is a product of an intricately designed computer program. It proposes that what we perceive as the physical world is a complex virtual construct, akin to some sort of hyper-advanced video game. Supporters of this theory argue that the rapid advancements in technology and computing power, along with our own efforts to create realistic virtual environments, point towards the feasibility of such a universe. They propose that an advanced civilization with incomprehensible computing capabilities could create a simulated reality that is indistinguishable from the real universe. Well, I've given you about 4 theories. If you know the names of these theories, make sure you comment their names below. Let's continue. You see, the universe is very strange. We've got particles popping in and popping out of existence everywhere. There's something, and then pop, nothing. We've got dark matter, a mysterious substance that makes up a significant portion of the universe's mass, but remains invisible to our current methods of observation. It does not emit, absorb, or reflect light, yet its gravitational effects can be observed in galaxies and the large-scale structure of the universe. We've also got dark energy, which seems to be expanding the universe with immense speed. Unlike gravity, which acts as an attractive force, dark energy seems to push galaxies apart, causing the fabric of space itself to stretch. This expansion occurs on such a grand scale that it surpasses the gravitational forces between galaxies, leading to an ever-widening cosmic expanse. And then we have the Big Bang, which tries to explain the origin and evolution of our universe. That the universe as we know it began from an incredibly hot and dense state approximately 13.8 billion years ago, suggesting that all matter, energy, space, and time originated from a singularity, a point of infinite density and temperature. In an extraordinary event, the universe rapidly expanded and continues to expand to this day. It was during this expansion that the fundamental forces and particles that govern the cosmos came into existence. But is it perfect? Did the Big Bang happen inside space, or was the Big Bang the beginning of space itself? Where did it happen, and how did it happen? Why did it happen in the first place? You see, the Big Bang Theory gives us a remarkable glimpse into the birth of our universe, but there are still many unanswered questions. We may have an idea of what happened after the Bang, but what happened before the Bang is where we are left hanging. How could all matter, energy, space, and time be packed into a point of infinite density and temperature? It boggles the mind. Strangely enough, some cosmologists entertain the idea that a previous incarnation of emptiness, a cold, dark, and empty universe, similar to the one awaiting us in the distant future, could have been the source of our very own Big Bang. This may sound confusing, but let me explain what I mean. First off, I want us to look at how the concept of material or physical matter came into existence. When we consider the origins of stable matter composed of atoms or molecules, it becomes clear that such matter did not exist during the initial stages of the Big Bang, nor for hundreds of thousands of years thereafter. The early universe was a hot and dense environment, filled with highly energetic particles that prevented the formation of complex matter. However, as the universe expanded and cooled over time, conditions became favorable for the formation of the first atoms. This process, known as nucleosynthesis, allowed simpler particles to combine and create stable atoms such as hydrogen and helium. But this understanding doesn't address the question of whether something came from nothing. Going further back in time, around 1/10,000th of a second after the Big Bang, the first long-lived matter particles, namely protons and neutrons, emerged. These particles form the building blocks of atomic nuclei. Prior to this crucial moment, there wasn't any material as we commonly understand it, but physics lets us keep on tracing the timeline backward to physical processes which predate any stable matter. This brings us to the fascinating era known as the Grand Unified Epoch. At this stage, we delve into the realm of speculative physics since our current experiments cannot generate enough energy to directly observe the processes that occurred during that time. Nonetheless, there is a plausible hypothesis that the physical world consisted of a swirling mixture of short-lived elementary particles, including quarks, which are the fundamental constituents of protons and neutrons. During this epoch, there existed both matter and its antimatter counterpart in roughly equal amounts. Each matter particle, such as a quark, had its antimatter counterpart, which was almost identical but differed in one aspect. However, whenever matter and antimatter encountered one another, they would instantaneously annihilate, transforming into pure energy. As a result, these particles were constantly being created and destroyed, a vibrant dance of matter and antimatter. But how did these particles come into existence in the first place? According to quantum field theory, even a seemingly empty vacuum, which corresponds to empty space-time, is teeming with dynamic energy fluctuations. These fluctuations have the potential to give rise to particles spontaneously appearing, only to vanish shortly thereafter. At first glance, this might seem like a peculiar mathematical phenomenon rather than something grounded in physical reality. However, the existence of such particles has been observed in numerous experiments, providing tangible evidence of their fleeting existence. The space-time vacuum state is a bustling realm where particles are continuously being created and annihilated, seemingly emerging out of nothing. However, this observation leads us to consider that the quantum vacuum, despite its name, is not an empty void, but rather a dynamic entity in its own right. This notion challenges the idea of getting something from nothing. Suppose we ask the question, where did space-time itself arise from? We find ourselves delving deeper into the distant past, reaching the ancient Planck epoch, a period so early in the universe's history that our best theories of physics break down. This era occurred only 1/10,000,000th of a trillionth, of a trillionth, of a trillionth of a second after the Big Bang. At this point, space and time themselves became subject to quantum fluctuations. Physicists ordinarily work separately with quantum mechanics, which rules the microworld of particles, and with general relativity, which applies on large cosmic scales. But to truly understand the Planck epoch, we need a complete theory of quantum gravity, merging the two. While we have yet to achieve a definitive theory of quantum gravity, scientists have made notable attempts through frameworks such as string theory and loop quantum gravity. Within these approaches, the conventional notions of space and time undergo a transformation. They are perceived as emergent phenomena, analogous to the rippling waves that manifest on the surface of a vast ocean. According to these theories, our familiar experience of space and time arises from underlying quantum processes occurring at a minuscule microscopic level. These processes, operating beyond our intuitive grasp as beings entrenched in the macroscopic world, present intriguing challenges to our understanding. In the Planck epoch, our ordinary understanding of space and time breaks down, so we can't even rely on our ordinary understanding of cause and effect either. Despite this, all candidate theories of quantum gravity describe something physical that was going on in the Planck epoch, some quantum precursor of ordinary space and time. But where did all of that come from? Even if causality no longer applies in any ordinary fashion, it might still be possible to explain one component of the Planck epoch universe in terms of another. Unfortunately, by now even our best physics fails completely to provide answers. Until we make further progress toward a theory of everything, we won't be able to give any definitive answer. The most we can say with confidence at this stage is that physics has so far found no confirmed instances of something arising from nothing. To truly answer the question of how something could arise from nothing, we would need to explain the quantum state of the entire universe at the beginning of the Planck epoch. All attempts to do this remain highly speculative. In 2020, renowned physicist Roger Penrose, a recipient of the Nobel Prize, introduced an intriguing yet controversial concept known as conformal cyclic cosmology to describe a cyclical universe. A cyclical universe is a model of cosmic evolution according to which the universe undergoes endless cycles of expansion and cooling, each beginning with a big bang and ending in a big crunch. Penrose was motivated by a fascinating mathematical relationship between the hot, dense, and small state of the universe during the Big Bang and the cold, expanded, and empty state it is predicted to reach in the distant future. His radical theory proposes that these states become mathematically identical when taken to their extreme limits. This paradoxical notion suggests that the complete absence of matter could potentially give rise to all the matter that exists in our observable universe today. In this perspective, the Big Bang emerges from what can be considered as almost nothing. This notion arises when all the matter within a universe is gradually absorbed by black holes, which eventually dissipate into photons and vanish into a vast void. Thus, the entire universe originates from a state that, when observed from an alternative physical standpoint, closely resembles absolute nothingness. However, even within this apparent nothingness, there exists a particular kind of something. It is still a physical universe, albeit one that is remarkably empty and devoid of traditional matter. How can the very same state be a cold, empty universe from one perspective and a hot, dense universe from another? The answer lies in a complex mathematical procedure called conformal rescaling, a geometrical transformation which in effect alters the size of an object but leaves its shape unchanged. Penrose demonstrated how the cold, dense state and the hot, dense state could be connected through this rescaling process, aligning their spacetime shapes while disregarding their sizes. It can be challenging to comprehend how two objects can be considered identical when they have different sizes, but Penrose suggests that size loses its conventional meaning in these extraordinary physical environments. The focus shifts towards understanding the fundamental nature of the spacetimes and the underlying connections between them, transcending the constraints of size as we typically perceive it. In conformal cyclic cosmology, the explanation unfolds in a unique manner, from the old and cold state to the young and hot state. The existence of the hot dense state is attributed to the cold empty state, but this because is not the usual cause and effect relationship we are familiar with, where one event follows another in time. In these extreme states, not only does size lose its significance, but so does time. The cold dense state and the hot dense state exist on different timelines, separated by their distinct temporal geometries. From the perspective of an observer within the cold empty state, it would persist indefinitely in its own timeline. However, the hot dense state that emerges creates a new timeline entirely, with its own distinct properties and evolution. It may help to understand the hot dense state as produced from the cold empty state in some non-causal way. Perhaps we should say that the hot dense state emerges from, or is grounded in, or realized by the cold empty state. These are distinctively metaphysical ideas which have been explored by philosophers of science extensively, especially in the context of quantum gravity, where ordinary cause and effect seem to break down. At the limits of our knowledge, physics and philosophy become hard to disentangle. Conformal cyclic cosmology provides us with intriguing and speculative insights into the origins of our Big Bang. However, even if Penrose's ideas are confirmed by future advancements in cosmology, we may find ourselves confronted with a deeper philosophical inquiry. This inquiry revolves around the origin of physical reality itself and raises the fundamental question of how the entire system of cycles came into existence. Ultimately, we are led to ponder one of the most profound questions in metaphysics. Why is there something rather than nothing? This question delves into the very nature of existence and challenges us to explore the mysteries of our reality at its most fundamental level. But our focus here is on explanations that remain within the realm of physics. There are three broad options to the deeper question of how the cycles began. It could have no physical explanation at all, or there could be endlessly repeating cycles, each a universe in its own right, with the initial quantum state of each universe explained by some feature of the universe before. Or there could be one single cycle, and one single repeating universe, with the beginning of that cycle explained by some feature of its own end. The latter two approaches avoid the need for any uncaused events, and this gives them a distinctive appeal. Nothing would be left unexplained by physics. Penrose envisions a continuous sequence of new cycles, driven in part by his interpretation of quantum theory. In quantum mechanics, a physical system exists in a superposition of multiple states simultaneously and only resolves into a specific state upon measurement. According to Penrose, each cycle involves random quantum events unfolding in unique ways, resulting in variations between cycles. This concept holds promise for experimental physicists, as it suggests the possibility of detecting remnants or anomalies from the previous universe that gave birth to our own. By studying the faint traces in the residual radiation from the Big Bang, observed by satellites like Planck, we may gain insights into the ancient universe that preceded ours. Penrose and his collaborators believe they may have spotted these traces already, attributing patterns in the Planck data to radiation from supermassive black holes in the previous universe. However, their claimed observations have been challenged by other physicists, and the jury remains out. Endless new cycles are key to Penrose's own vision. But there is a natural way to convert conformal cyclic cosmology from a multi-cycle to a one-cycle form. Then physical reality consists of a single cycle around through the Big Bang to a maximally empty state in the far future, and then around again to the very same Big Bang, giving rise to the very same universe all over again. This notion aligns with an alternative understanding of quantum mechanics called the many worlds interpretation. According to this interpretation, when we measure a system in a superposition, the result we observe is not a random selection. Instead, it represents just one possibility that unfolds in our own universe. In the many worlds interpretation, each of the other measurement outcomes plays out in separate parallel universes within a vast multiverse, entirely disconnected from our own. Therefore, no matter how improbable an event may be, if it has a non-zero probability, it occurs in some quantum parallel world. In these other worlds, there are individuals similar to you who have won the lottery, been caught up in unusual typhoons, spontaneously combusted, or even experienced all three events simultaneously. Our Big Bang might be the rebirth of one single quantum multiverse, containing infinitely many different universes all occurring together. According to some theories, parallel universes could leave traces in the data we observe from the cosmos, such as signs of collisions between our universe and others. This idea connects with the concept of many worlds quantum theory, although not everyone agrees, including Penrose. In this view, our Big Bang could mark the beginning of a vast quantum multiverse where countless universes coexist simultaneously. In this multiverse, every possible event and outcome takes place, repeating endlessly in a cycle of existence. It suggests that everything imaginable not only happens once but occurs repeatedly, creating a rich tapestry of infinite universes. Okay, to understand how the universe came from nothing, we need to delve into its nature. Our universe operates in two fundamental ways, which shape the fabric of reality and provide insights into its origins. The first mode is the deterministic nature of the universe. Determinism suggests that every event and outcome in the universe is governed by a set of predetermined conditions and the laws of nature. This viewpoint posits that if we possess complete knowledge of the initial state of the universe and the governing laws, we can predict the future trajectory of events with certainty. Determinism provides a sense of order and predictability, offering a foundation for scientific inquiry and understanding. However, as we explore deeper into the mysteries of the universe, we encounter the second mode of operation, the probabilistic nature of the universe. This aspect, prominently observed in the realm of quantum mechanics, introduces inherent randomness and uncertainty into the fabric of reality. At the subatomic level, particles and their properties exhibit probabilistic behavior, where outcomes are expressed as probabilities rather than definite predictions. This probabilistic nature challenges the strict determinism of classical physics and brings to light the fascinating realm of quantum indeterminacy. The interplay between determinism and probability raises profound questions about the nature of the universe and its origins. How do these two modes coexist? Can determinism fully explain the complex emergence of our universe from nothingness, or does the probabilistic nature of quantum mechanics play a role? Exploring these questions allows us to peer into the fundamental nature of reality itself. Determinism, as we have discussed, proposes that every event and outcome in the universe is predetermined by a set of initial conditions and the laws of nature. In the context of the universe coming from nothing, determinism provides a framework for exploring the sequence of events that could have led to its existence. At the earliest moments of the universe, we imagine a state of absolute nothingness. In this hypothetical scenario, there is no matter, energy, or even space and time as we know them. However, according to determinism, there must have been a specific set of initial conditions that set the stage for the universe's emergence. These initial conditions could involve various factors, such as the properties of the singularity, the values of fundamental constants, or even the existence of additional dimensions beyond our current understanding. The exact nature of these initial conditions is still a subject of intense scientific investigation and speculation. According to determinism, the evolution of the universe is governed by the laws of physics, such as general relativity and quantum mechanics. These laws dictate how matter, energy, and space-time interact and evolve over time. By understanding these laws and the initial conditions that set the stage for the universe's existence, we can trace the sequence of events that led to its formation. As the universe expands, matter and energy undergo various transformations and interactions. Particles emerge, forces come into play, and structures begin to form. Through the interplay of gravity, electromagnetism, and the strong and weak nuclear forces, galaxies, stars, and planets take shape over vast cosmic timescales. Determinism allows us to conceive of this cosmic symphony as a deterministic process, where each stage of the universe's evolution is intricately connected to the preceding conditions and governed by the laws of nature. The properties of matter, the formation of galaxies, and the emergence of life can be seen as the inevitable outcomes of this grand deterministic unfolding. Moreover, determinism offers an explanation for the fine-tuning observed in the universe. The fundamental constants and physical parameters, such as the strength of gravity or the masses of particles, appear to be precisely adjusted to allow the existence of complex structures and life. Determinism posits that these finely tuned values are not mere coincidences, but the result of the deterministic unfolding of the universe from its initial conditions. On the other hand, we have the probabilistic nature of the universe, which introduces a realm of inherent randomness and uncertainty into the fabric of reality. In the realm of quantum mechanics, the probabilistic nature of the universe becomes particularly prominent. At the subatomic level, particles and their properties do not follow strict determinism, but rather exhibit probabilistic behavior. This means that the outcomes of certain measurements or observations are expressed as probabilities, rather than definite predictions. One of the key concepts in quantum mechanics is the wave-particle duality. It suggests that particles, such as electrons or photons, can exhibit both wave-like and particle-like behavior. When it comes to observing the properties of these particles, such as their position or momentum, their behavior becomes inherently uncertain. The famous Heisenberg uncertainty principle captures this fundamental uncertainty. It states that there is a limit to how precisely we can simultaneously know certain pairs of properties, such as position and momentum or energy and time. The more accurately we try to measure one of these properties, the less precisely we can know the other. This inherent uncertainty is not due to limitations in measurement, but is a fundamental characteristic of the probabilistic nature of the universe. The probabilistic nature of quantum mechanics becomes further pronounced through phenomena such as superposition and entanglement. Superposition refers to the ability of particles to exist in multiple states simultaneously until they are observed or measured. This implies that before observation, a particle can be in a state of being in multiple places or having multiple properties at once. Entanglement, on the other hand, refers to the mysterious correlation that can exist between particles, even when they are separated by vast distances. When particles become entangled, their properties become linked, and changes in one particle instantaneously affect the other, regardless of the distance between them. This non-local and seemingly instantaneous connection challenges our intuitions about causality and further highlights the probabilistic nature of the universe. The probabilistic nature of the universe poses intriguing questions about the role of chance and randomness in its emergence. Could it be that the initial conditions that led to the universe coming from nothing were themselves subject to probabilistic fluctuations? Did chance play a role in the precise values of fundamental constants and the emergence of the conditions necessary for the development of life? These questions push us to explore the interplay between determinism and probability in understanding the universe's origins. While determinism provides a framework for tracing the evolution of the universe from its initial conditions, the probabilistic nature suggests that chance and randomness may also play a significant role in shaping the course of events. These two perspectives offer complementary lenses through which we can explore the intricate fabric of reality, yet they often appear as separate strands, awaiting a unifying thread that can weave them together into a comprehensive tapestry. These two perspectives, determinism and probability, seem to occupy separate realms of understanding. Determinism provides order, predictability, and a sense of causality, while probability introduces chance, unpredictability, and the intrinsic fuzziness of reality. They appear as distinct entities, awaiting reconciliation and a unifying framework. The challenge lies in reconciling these seemingly divergent perspectives, bridging the gap between the deterministic and the probabilistic. At the crossroad of these theories, we find ourselves in what physicists call the theory of everything or the final or ultimate theory. The theory of everything represents a profound quest for a unified framework that can encompass both determinism and probability, providing a comprehensive understanding of the universe. It seeks to harmonize the precise order of deterministic laws, such as general relativity, with the inherent randomness and uncertainty of quantum mechanics. This endeavor aims to reveal a deeper synthesis where the deterministic and the probabilistic coexist, enriching our understanding of the nature of reality. In the pursuit of a theory of everything, scientists and theorists explore various avenues, including string theory, loop quantum gravity, and other quantum gravity frameworks. These approaches strive to merge the deterministic laws governing large-scale phenomena with the probabilistic behavior of particles at the quantum level. They seek to uncover the unifying principles that underpin the fabric of the universe, from the majestic dance of galaxies to the subatomic interplay of particles. Yet, the path to a theory of everything remains an ongoing endeavor, filled with challenges and open questions. The intricate nature of quantum gravity, the enigma of space-time, and the puzzle of unifying fundamental forces present complex frontiers that continue to be explored. Nevertheless, the quest for a theory of everything is driven by the recognition that the deterministic and the probabilistic aspects of the universe are not mutually exclusive. They are intertwined threads waiting to be woven into a coherent narrative. Through the unification of these perspectives, we strive to unravel the deepest secrets of existence, to understand how the deterministic laws and the probabilistic nature coalesce, and to grasp the underlying fabric of the cosmos. If the Big Bang Theory is true, how did it lead to all the planets, stars, and galaxies we can see today? Thanks to a series of calculations, observations from telescopes on Earth and probes in space, our best explanation is this. Around 13.8 billion years ago, all the matter in the universe emerged from a single minute point, or singularity, in a violent burst. This expanded at an astonishingly high rate and temperature, doubling in size every 10 to minus 34 seconds, creating space as it rapidly inflated. Gravity and all the other forces were formed within a tiny fraction of a second. The energy changed into particles of matter and antimatter, which largely destroyed each other. But luckily for us, some matter survived. Protons and neutrons started to form within the first second. Within minutes, these protons and neutrons could fuse and form hydrogen and helium nuclei. After 300,000 years, nuclei could finally capture electrons to form atoms, filling the universe with clouds of hydrogen and helium gas. After around 380,000 years, it left behind a bath of photons, the cosmic microwave background that Penzias and Wilson accidentally detected. Within this were tiny ripples of matter that were stretched to enormous sizes during inflation, and in turn, these became the seeds for the galaxies and galactic clusters we see today. Today, when we look out at the universe, the full suite of observations we've collected, even with the known uncertainties taken into account, all point towards a remarkably consistent picture. Our universe is made of matter, obeys the same laws of physics everywhere and at all times. It's governed by general relativity, it's expanding and cooling and gravitating, and it's dominated by dark energy and dark matter, with normal matter, neutrinos, and radiation making up the rest. Today, it's full of galaxies, stars, planets, heavy elements, and intelligent and technologically advanced life in at least one location. These structures weren't always there, but instead arose as a result of cosmic evolution. In a remarkable scientific leap, 20th century scientists were able to reconstruct the timeline for how our universe went from a mostly uniform universe, devoid of complex structure and consisting exclusively of hydrogen and helium, to the structure-rich universe we observe today. If we start from today, we can step backwards in time and ask where any individual structure or component of that structure came from. For each answer we get, we can then ask, okay, but where did that come from? And how did that arise? Going back until we're forced to answer, we don't know, at least not yet. Then, at last, we can contemplate what we have and ask, how did that arise? And is there a way that it could have arisen from nothing? To begin with, the life we have today comes from tiny particles that make up everything around us. These particles are like building blocks, and they join together to make complex molecules, which are the ingredients for life. These building blocks are made of even smaller parts called atoms. The atoms are like the basic elements that make up everything in the universe. But these atoms didn't just appear when the universe began. They needed a long process to form. This process involves stars being born, living their lives, and then dying. When stars die, they create new materials through powerful reactions. These materials are then used to make new stars, and the cycle continues. This cycle is necessary for things like planets and complex chemistry to exist. For the universe to have stars and galaxies like we see today, a few important things had to happen. Gravity had to pull smaller groups of stars and galaxies together to form larger ones. This required having some mass to start with, which gathered more mass due to gravity. To prevent matter from being lost into space during star formation, something called dark matter had to be present in the early stages. The right balance of different types of matter and radiation was needed to create things like the glow left over from the Big Bang and the basic elements. To make galaxies and other structures, there needed to be slight variations in the density of matter, and these variations grew over time because of gravity. The initial imbalances in density, along with the creation of dark matter and normal matter, were essential to make everything we see. So, when we think about whether the universe could come from nothing, these are the important things that we don't fully understand yet. Physics usually treats matter and antimatter equally, meaning reactions create or destroy both in the same amounts. At the universe's start, matter and antimatter could have been made in huge quantities due to its extreme heat and density. But somehow, the universe ended up having more matter than antimatter, even though they should have been equal. There are different ways this could have occurred, although we're not certain which happened. All these ways involve three main things: special conditions where things aren't balanced, which happens as the universe expands and cools; processes that break the usual rules and allow interactions that create more matter than antimatter. The standard model of physics allows for this through something called Sphaleron interactions, a way to create enough of a certain type of violation that helps make more matter than antimatter. The standard model includes these ideas, but they aren't enough by themselves. If you think of a universe with equal matter and antimatter as a universe with nothing, then it seems our universe did create something from nothing, even though we're not entirely sure how it happened. Likewise, there are various ways to create dark matter. We've determined through a lot of testing and research that dark matter can't be made of the particles found in the standard model of physics. Whatever dark matter is, it calls for new physics beyond what we currently know. Different possibilities exist for how it could have formed, such as being made during the early, hot phase of the universe and then not completely disappearing, so it remains stable. Forming during a phase change as the universe expanded and cooled, where big particles come out of nowhere, existing as a different type of neutrino, which could mix with regular neutrinos or be a heavier kind alongside the usual ones, coming about solely due to gravity, creating an extremely heavy particle. Why do we have dark matter today when the rest of the universe seemed to function fine without it in its early stages? There must have been a way to create this thing when it didn't exist before. However, all these possibilities need energy. So the question is, where did all that energy come from? Perhaps according to cosmic inflation, our leading theory of the universe's pre-Big Bang origins, it really did come from nothing. When we picture the very start of the hot Big Bang, we're thinking of something super hot, crowded, and full of energy. Now, when we wonder how this all came about, there are two ways to think about it. First, we can simply say that the universe was born this way. This means the initial conditions were set like this, and we don't have a further explanation. In the world of theoretical physics, we call this approach giving up. Alternatively, we can do what theoretical physicists love to do: come up with a theory to explain those initial conditions. We work to make predictions that are different from what the current accepted theory says, and then we go out to test those predictions. Enter cosmic inflation, which came from this second approach and changed how we see the birth of the universe. Instead of imagining the hot and dense start as an infinitely tiny, infinitely hot point, inflation proposes that before the hot Big Bang, there was a phase where space itself had an incredibly high energy density. This caused the universe to expand extremely quickly during inflation. When inflation ended, that energy turned into matter, antimatter, and radiation, creating what we recognize as the hot Big Bang aftermath. In more detail, this inflation not only makes a universe with the same temperature everywhere and a flat appearance, but also predicts specific kinds of variations in density. When we observed these variations, they matched what inflation predicted. From almost empty space, though it's space full of energy, a natural process has crafted the entire universe we can see today, full of structures. This is the big idea of how we could get a universe from seemingly nothing, although not everyone finds it completely satisfying. For many people, it's hard to imagine a universe without space, time, and the rules of physics. We can think of a place outside space, a moment beyond time, or conditions that aren't bound by physical reality. These thoughts make sense if we consider these aspects as things we'd need to remove to reach a true state of nothingness, at least from a philosophical standpoint. However, there's a difference between philosophical nothingness and a more scientific view of nothingness. There are 4 scientific ways to define nothing, each valid in its own context. A time when something didn't exist. An empty space. Space-time in its emptiest state, with the lowest possible energy. Whatever remains when you remove the entire universe and its governing laws. If we use the first 2 definitions, we can say we've started with nothing and created a universe. But if we consider the 3rd definition, it's not so clear. Unfortunately, we lack enough knowledge to say anything about the 4th definition. Without a scientific theory describing what exists beyond the universe and the laws that apply there, the idea of true nothingness lacks a clear physical definition. In the context of physics, it's impossible to make sense of an idea of absolute nothingness. What does it mean to be outside of space and time? And how can space and time sensibly, predictably emerge from a state of non-existence? How can space-time emerge at a particular location or time when there's no definition of location or time without it? Where do the rules governing quanta, the fields and particles both, arise from? This line of thought even assumes that space, time, and the laws of physics themselves weren't eternal, when in fact they may be. Any theorems or proofs to the contrary rely on assumptions whose validity is not soundly established under the conditions which we'd seek to apply them. If you accept a physical definition of nothing, then yes, the universe as we know it very much appears to have arisen from nothing. But if you leave physical constraints behind, then all certainty about our ultimate cosmic origins disappears. Many scientists suggest that the universe might have emerged from nothing, an idea rooted in quantum theory. This notion hinges on the concept that quantum fluctuations could trigger the spontaneous creation of a universe out of nothingness. However, this idea lacked solid support due to the absence of mathematical evidence. Enter Dongshan. He and his team from the Wuhan Institute of Physics and Mathematics. They've made a significant contribution by offering the first mathematical proof that the Big Bang could indeed be a result of quantum fluctuations. Central to this breakthrough are the Wheeler-DeWitt equation and the Heisenberg uncertainty principle. The Wheeler-DeWitt equation marks a significant step in the quest for a theory that encompasses everything. Back in the 1960s, John Wheeler and Bryce DeWitt created a mathematical framework that blends quantum mechanics and general relativity. This equation contributes to our understanding of quantum gravity, a key challenge in merging gravity and quantum mechanics. However, the equation's main flaw is that it doesn't involve time, so it's not a complete unification, but it's the best we have so far. On the other hand, Heisenberg's uncertainty principle is more widely recognized. In simple terms, this principle states that you can't precisely know both the position and momentum of a tiny particle. Otherwise, you'd break some important physics rules. From this principle, we realize that empty space isn't truly empty. In the vacuum, particles can briefly pop in and out of existence due to random quantum fluctuations. This concept also relates to the idea of the false vacuum. So, how does all of this come together to help us? Dongshan explained it like this. We showed that once a tiny true vacuum bubble is formed, it has the potential to rapidly expand. The WIPM team describes these true vacuum bubbles as perfectly round spheres. They use this knowledge to determine how quickly the sphere's radius can grow. They go on to analyze the bubble in 3 possible space-time geometries: open, closed, or flat. Interestingly, they found that the bubble's expansion would lead to a Big Bang. This new equation provides fascinating insights into the universe. The theory proposes that dark energy, the force driving the universe's expansion, could be linked to a concept called quantum potential. Quantum potential is a component of the pilot wave theory, a less-known interpretation of quantum mechanics that offers an alternative or complement to our current understanding of quantum theory. Pilot wave theory aligns with existing quantum predictions, resolves paradoxes like Schrödinger's cat, and introduces the idea of quantum potential. One of the drawbacks of pilot wave theory has been its inability to make distinct predictions. All its predictions are either identical to the widely accepted quantum theory or are not testable. That's where the new derivation from WIPM, enters the picture. With quantum potential being a key element of this new equation, scientists might revisit the pilot wave theory. This fresh perspective could potentially advance our understanding of the universe by providing unique insights that go beyond what conventional quantum theory offers. Imagine a scenario where our universe wasn't born from a traditional Big Bang, but from a colossal collision between two gigantic, unseen objects in a higher dimensional realm. This is the essence of the ekpyrotic universe theory. In this theory, our universe isn't just the familiar 3 dimensions of space and 1 of time. Instead, it's a 4-dimensional brain that exists within a higher dimensional space. Think of this brain as a sort of cosmic sheet, floating in a larger reality that we can't directly perceive. The name ekpyrotic comes from ancient Greek, referring to a fiery, cataclysmic event. Just as a collision between 2 vehicles can create a massive release of energy, the collision of 2 brains in the higher dimensional space generates a burst of energy and matter that gives birth to our universe. This collision is like a spark that ignites the expansion and evolution of everything we see around us. This theory offers an intriguing alternative to the popular inflationary model of the universe's birth. The inflation theory suggests that the universe underwent a rapid expansion phase, driven by a mysterious field. But in the ekpyrotic scenario, it's not just the expansion, it's the result of a dynamic interaction between these higher dimensional brains. This concept doesn't just change how we think about the universe's beginning, it also introduces the idea of cyclical patterns. The ekpyrotic universe theory proposes that this collision isn't a one-time event. Instead, it suggests that our universe could be just one cycle in an ongoing series of collisions and expansions, with each cycle potentially leading to the birth of a new universe. Maybe the universe is a result of a colossal cosmic experiment conducted by an advanced civilization in a higher dimension. They created our universe as a simulation to study the emergence of life, matter, and fundamental forces. Maybe the universe is a mesmerizing projection that emanates from a higher dimensional realm, a concept that leads us to contemplate the profound idea that our reality is but a holographic reflection of an immensely intricate and multifaceted existence. Maybe the universe is a self-aware entity, a cosmic consciousness that came into being to experience existence in its myriad forms. This universe consciousness evolves through galaxies, stars, and living beings, accumulating knowledge and understanding along the way, like a universal self-discovery journey. Maybe space is like a phoenix in an eternal cycle of life and death. Maybe time repeats itself in an infinite recurrence of the universe after universe. Or perhaps this is the only universe after all, with a small hot beginning and a cold, dark finale, until the day comes when we discover how to extract more information from the universe than presently seems possible. We have no choice but to face our ignorance. The Big Bang still happened a very long time ago, but it wasn't the beginning we once supposed it to be. Imagine if we went back to when our solar system first formed and replayed that moment a billion times. It's very unlikely that humans would appear even once in those scenarios. But if we look back to the early stages of the hot Big Bang, a universe filled with stars, galaxies, planets like Earth, and countless opportunities for life to emerge becomes almost certain. This is because the rules and basic stuff of the universe stay the same. A universe born with certain materials will create specific elements. One with unevenness in density will make the first stars. The presence of dark matter will lead to stars with heavy components. When there's a second generation of stars, it results in planets like Earth and stars like our Sun. And when you have Earth-like planets, the possibility for life to thrive for a very long time appears. The rest might be influenced by randomness, but that's what allowed us to come into existence. It's now our responsibility to make the most of it. This video would not be complete without delving into the philosophical side of the topic. While we have already explored scientific and cosmological perspectives on the origins of the universe, it is essential to consider the philosophical arguments that have shaped our understanding of how something could emerge from nothingness. When contemplating the philosophical question of how the universe came from nothing, various arguments and theories have been put forth throughout history. These perspectives offer insights into the nature of existence, causality, and the very fabric of reality itself. One influential philosophical argument is rooted in classical metaphysics, where the principle of ex nihilo nihil fit is often invoked. This Latin phrase translates to out of nothing, nothing comes. Philosophers who adhere to this principle, such as Parmenides of Elea, question the very possibility of something emerging from absolute nothingness. They challenge us to consider alternative explanations or underlying principles that could account for the existence of the universe. Another prominent philosopher who contributed to this discourse is Gottfried Wilhelm Leibniz. Leibniz pondered the question of why there is something rather than nothing, and he proposed the principle of sufficient reason. According to Leibniz, everything that exists must have a sufficient reason or explanation for its existence. This principle invites us to search for a deeper underlying cause or rationale behind the emergence of the universe. These philosophical arguments highlight the profound metaphysical implications of the universe coming from nothing. They encourage us to critically analyze our assumptions, question the nature of causality and existence, and explore alternative explanations beyond scientific and cosmological frameworks. By considering the philosophical dimension of the topic, we gain a broader perspective that goes beyond empirical evidence and scientific theories. It prompts us to engage in deeper reflections on the fundamental nature of reality and existence itself. And there you have it, a thought-provoking exploration of the origin of the universe and its fine-tuned nature. We have ventured through scientific, philosophical, and metaphysical perspectives to delve into the mystery of how the universe could have emerged from nothingness. Philosophy has enriched our understanding by introducing arguments such as the teleological perspective, which suggests an intelligent designer or grand cosmic plan, and existentialist philosophies which explore the subjective meaning we create in a seemingly indifferent universe. These philosophical insights remind us of the broader implications and existential significance of our inquiries. Furthermore, we have contemplated the probabilistic and deterministic nature of the universe, recognizing the interplay between chance and order, and the ongoing pursuit of a unified theory that can reconcile these seemingly divergent perspectives. Throughout our exploration, one thing becomes clear. Our quest for understanding the origin of the universe is far from complete. The more we uncover, the deeper the mysteries become. The notion that the entire universe came from nothing challenges our intuition and invites us to contemplate the fundamental nature of reality itself. As we continue to seek answers, it is important to remain open-minded and embrace the awe-inspiring complexity of the universe. Whether through scientific inquiry, philosophical contemplation, or the integration of diverse perspectives, we are driven by an insatiable curiosity to unravel the secrets of our cosmic origins. Hopefully, by nurturing our collective curiosity, fostering interdisciplinary collaborations, and nurturing a sense of wonder, we will inch closer to unlocking the enigmas of existence. As we traverse the uncharted territories of knowledge, let us embrace the grandeur of the questions that lie before us. Thanks for watching today's video, and I'll see you in the next one.
Exploring the unknown has been a challenge for explorers over the centuries. As the machines blaze a trail across the solar system, we can see the sun, moon, and planets with more clarity than ever. It is as though their cameras are our windows on an extraordinary journey. We can see the cosmos through their eyes. Thanks to the invention of spaceflight, we have access to a variety of alien worlds and new territories. The night sky has been a window to a larger reality since the dawn of humanity. According to our ancient ancestors, the heavens above were evidence of something beyond. They were inextricably linked to life on Earth. Our ancestors observed the sky night after night and year after year, wondering what those changes might foretell about their destiny. There were a few changes that were easily observed. Constellations drift from east to west, like the nightly drift of the constellations. This is like the lunar phases of the moon that march from east to west. In addition, there were more fleeting changes, like colourful aurora borealis displays. From our ancestors, no change attracted as much attention as the complex dance of a few sharp objects moving around among the constellations. Although they looked like stars, their motions made it clear they were not. In Greek, they were called planets or wanderers. Throughout history, astronomers have puzzled over the motions of these planets and attempted to understand how our universe works. We could not see how particular the planets are without the invention of the telescope. When the telescope arrived, it opened up a whole new view of the universe, transforming the planets into distant worlds orbiting around the sun from just lights moving in the sky. It helped us understand that we are part of a solar system full of planets, asteroids, comets, and more. Any telescope can only show us a limited amount of the solar system. What happened next was the most exciting part of Loaded and Verified. A breakthrough technology was poised to reveal the planets to us like never in the 1960s. Because of spaceflight, it was no longer necessary to have better views of distant planets. Instead, you could see moving planets through the windows. Scientists on Earth got a taste of what it would be like to visit an alien world from this experiment. The first space voyages beyond Earth were directed at our nearest neighbor, the Moon. Soon, space probes crossed the great ocean of interplanetary space and sent back images of Mars and Venus. In addition, the first images of the hidden far side of the Moon were taken by the Soviet spacecraft Luna 3. The possibilities were endless. Mercury's surface has also been baked by the Sun. NASA research even farther to the distant outer planets in the 1970s and 80s. The most famous mission, Voyager 2, visited 4 giant planets in a row, including Jupiter, Saturn, and Uranus, before reaching Neptune in 1989. In recent years, the second wave of missions has allowed us to see the solar system from new perspectives and provided us with a robust new understanding of many planets. Sometimes that perspective means more detail and complexity than we ever imagined, such as these cloudy swirls in Jupiter's turbulent atmosphere. The icebergs could also be on Jupiter's moon, Europa's surface. There have been other cases where spacecraft revealed more history than we could have imagined in this barren Martian desert crater. The rim of the crater contains layers of ancient rock. These layers have been read like pages of a novel by geologists, and the story they tell describes long-vanished waters that once dissolved an alien landscape. The rich information, perspectives, and valuable data we receive from so many planetary missions show how diverse our solar system is. Additionally, we know that these very different places in the solar system have a common origin. The evidence shows that our Sun was born from an interstellar cloud of gas and dust some 4.5 billion years ago. Today, we can observe the same process in our Milky Way galaxy with the Hubble Space Telescope. We see what appears to be a gorgeous nebula of glowing gas, but it is actually a star factory, and our Sun was born there. There are unique characteristics for each member of our solar system family. As matter swirled together to form our newborn star, the Sun was not created in isolation. This matter ended up in a disk of gas and debris spinning around the infant Sun. Planets, moons, asteroids, and comets were born from the disk, like different children of the same parents. How did these solar system objects take different paths from the same essential ingredients? This is one of the big questions in planetary science. There was only one pathway that led to Earth, as far as we know. The Earth has the potential to sustain life. That life has been protected by it. After experiencing this, I began wondering about the solar system. We will not stop exploring. Our journey will also end at the starting point, knowing where we are. All the planets in our solar system share these traits. All the moons, all the asteroid bodies. Putting together these stories will also help scientists understand how we got here. On our own, at our own pace. We all face these questions. How we go about addressing them is described as well. The process has begun. Our solar system has many epic and beautiful destinations waiting to be explored, but none is more terrifying or beautiful than this hellish realm of searing, writhing, and dancing fire. We're talking about a vast and volatile powerhouse whose explosive explosions can reach thousands of miles into space, rattling our tiny world. The Sun is our star. Our entire living world and civilization depend critically on its power. Life as we know it would not be possible without the Sun's warmth and light. Even in ancient times, they regarded it as God. Our Milky Way galaxy is filled with hundreds of billions of stars, including the Sun. For us, the Sun is the most important star. Our solar system has 8 planets. several dozen moons, hundreds of thousands of asteroids, and possibly trillions of comets. Despite this, there is only one sun, and it is 1,000 times more massive than the rest of our solar system combined. Everything is kept in orbit by the gravity of the sun. The sun always takes center stage wherever you are in the solar system. Galileo, a 15th century astronomer, was convinced our solar system was centered on the sun, not the Earth. To defend his radical view, he was tried for heresy. Besides pointing a telescope at the sun, Galileo made another surprising discovery. The sun sometimes develops dark patches that seem to drift across the surface of its blazing surface. Eventually, astronomers learned that a subtle pattern governs the appearance of sunspots. On either side of the sun's equator, they increase in number over an 11-year cycle. They cover all regions of the solar surface as they extend north and south. Each reaches its peak and then diminishes, and the cycle starts. It is clear from sunspots that our solar system is not just a simple light bulb, but a dynamic and complex one. There were hints that the sun is more than meets the eye, even before Galileo's time. The most obvious occurs every time the moon passes directly in front of the sun, resulting in a total eclipse. An eclipsed sun is surrounded by a glowing cloud of white light called the solar corona. In the highly ionized outer atmosphere of the sun, ionized gas is energized to a much higher temperature than at the surface. The corona is also constantly changing, just like sunspots. Scientists could not explain where the sun's energy initially comes from for generations, because these clues suggest it releases its energy in complicated ways. An unexpected side effect of the atomic age followed. Scientists have discovered how sunlight is produced by discovering nature's hidden nuclear forces. The sun is mainly made up of hydrogen gas at its surface. As with most stars in the universe, the gas is about 5,600 degrees Celsius, hot enough to emit a bright yellow light. Temperatures reach millions of degrees in the sun's core, and hydrogen atoms can combine to form helium under these extreme conditions. As energy is released from the sun's core through overlaying layers, it gradually escapes into space. Our planet receives only a tiny fraction of the sun's total energy. Suns are not always benevolent, as there is ample evidence to prove it. It has remained steady for eons, allowing life on Earth to flourish. Solar flares, which produce dazzling aurora borealis displays and giant explosions on the sun, have long been known to scientists. For scientists to understand the sun's changeable nature and how it influences the Earth, they must venture into space. It is possible to observe the sun around the clock, and in ways not possible from the ground. As a result, astronomers have been able to study the rotational surface of the sun over a long period. Using a circular disk to block the sun's light is a less direct method of studying solar activity from space. Creating an artificial eclipse inside the spacecraft makes it easier to observe dramatic changes in the sun. This method was used for years by the SOHO spacecraft. Comet-like particles are hurled at SOHO by a swoop of high-energy particles. Occasionally, a vigilant spacecraft will catch a trespasser. A transit of Mercury across the sun can be seen here. Space views reveal an incredibly dynamic sun connected from surface to corona by an invisible force, magnetism. Magnetism is the most potent force in the solar system. As a turbulent, electrically charged fluid, the sun is not a solid body. The motions of that fluid create the sun's magnetic field. Fields such as this poke through the solar surface and form loops that extend into space. Sunspots are created when material that would typically turn over and sink back into the sun's interior is temporarily held at its surface and allowed to cool and darken. Solar magnetic fields can store enormous energy in their loops and twists. This energy is released rapidly and violently. Solar flares are the result. SOHO captured these photos of one of the most powerful solar flares in history on October 29, 2003. A vast region of magnetic activity first appears on the left-hand side of the sun. As high-speed charged particles hit the spacecraft's camera, this region gradually moves toward the center of the sun, where it explodes in a flash of light and burst of static. But a powerful solar flare can quickly destroy it. A coronal mass ejection is another hazard often associated with solar flares. As a result, there is a massive release of magnetically energized particles from the Sun's corona. Once they encounter Earth, the particles travel at high speeds through space. Particles cascade onto the atmosphere around the north and south poles, producing brilliant auroras. We have learned that the Sun is not an isolated and distant part of our solar system because of the age of space exploration. Earth travels through the Sun instead, and it is not just Earth that experiences this. The Sun is beside our planet and all other planets in our solar system. As a result, we are separated from the flow of interstellar material that permeates the galaxy with the Sun by a giant bubble. It is not just a star that we have. Stars surround us. As children of the Sun, there is also a connection between us. Each planet was created from the same primitive mix of atoms that formed the Sun billions of years ago. Since then, each planet has gone its way, sharing its own unique story. Discovering what lies beyond the horizon has challenged explorers for generations. In spaceflight, we explore alien worlds and discover vast new territories. The intrepid machines blazing a trail for us across the solar system today allow us to see the Sun, Moon, and planets with penetrating clarity. Through their cameras, we have been granted unprecedented access to the universe that they have discovered. To the human eye, our universe comprises light. It is the sign that matter is found in stars, galaxies, and vast expanses of glowing gas. Life cannot exist in this colourful world of gas and stars. The sweltering temperatures in space that produce gaseous glow are too extreme for life to survive. A strange environment is what life needs. It needs solids instead of gases. Rocky planets are ideal for life. There is no guarantee that life will take root because you have a solid foundation. There are many rocky worlds in our solar system. It would be impossible for life as we know it to exist without planets made of rock. Mercury is first on our list. It rotates slowly in the glare of the Sun, alternately baking and freezing. Mercury is the closest planet to the Sun, and its surface temperature can reach over 420 degrees Celsius during the day. The temperature can drop to minus 180 on the planet's night side, when the heat is rapidly radiated into space during long months of darkness. Until the beginning of the 21st century, Mercury's only visitor was the Mariner 10 spacecraft. We got to see Mercury's battered and baked surface up close for the first time. Mercury aims to orbit it and conduct the first comprehensive survey of its geological features and mineral composition. The spacecraft's view of the planet was incomplete, since less than half was visible. NASA launched Mercury Messenger in 2004. Messenger's images, at first glance, seem to depict a desolate lunar landscape. Mercury's surface was blasted by an enormous crater-forming impact, kicking up debris. Among the craters are some giant cliffs and escarpments. Mercury is known for them. The wrinkles may have formed because of the planet's giant metal core cooling and contracting. In Messenger's first images of Mercury, one can see only the bare bones of a rocky world. Over eons of geological time, nothing much has changed here, except the surface. This planet does not have an atmosphere. Mercury may provide some beginnings of a stable platform, but it is far too hot and barren to be anything other than an empty stage. In order to turn a dead planet into a living one, more than just an atmosphere is needed. Another rocky world, Venus, is mysterious. Venus was hidden from astronomers for centuries because of its dense, cloudy atmosphere. We now know that Venus's atmosphere consists mainly of carbon dioxide with sulfuric acid clouds. The Sun's energy is trapped by carbon dioxide, heating the planet to a staggering 466 degrees Celsius, making it even hotter than Mercury. The air pressure on the surface of Venus, even though Venus is twice as far from the Sun and its atmosphere is extremely dense, is so high that it would easily crush a human astronaut to death. It is easy to be deceived by first impressions. Countless meteorite impacts over billions of years have left the surface rough and heavily cratered. Mercury is so heavy that it is probably almost entirely composed of metal. Mercury's mass is twice as great as our Moon, even though it is slightly larger. Scientists have speculated that Mercury was a much larger planet whose exterior was shattered mainly by a collision. The result was a thin, rocky mantle surrounding a substantial metallic core. Mercury once bubbled and rumbled with the heat coming from a tumultuous internal formation. Several features show a volcanically active past. Underneath the more recent impact craters, we can see multiple ripples. Waves on the surface were frozen in time to reveal vast pools of lava that had once covered the planet. A blue area represents an ancient terrain gradually buried by orange-red debris. This image emphasizes Mercury's long history via false colors. Venus's extreme conditions have only allowed a handful of Soviet landers to take brief glimpses of its surface, none of which have survived for over 2 hours. Scientists had to devise other ways to explore Venus's remote terrain, with a planet so inhospitable to spacecraft. Radar can penetrate the cloud cover and bounce off the rock below, providing a detailed view of the planet's bizarre and dramatic landscape. Images like these reveal a volcanic world that may still be active today. Venus's surface appears to be black impact craters, which differ from what we see on Mercury, which shows that Venus is young and is likely to be continuously developing. Scientists now suspect that Venus might have been more like our planet in the past. Despite this, Earth's atmosphere warmed, destroying a vital part of its uniqueness. There is water in it. Our planet's oceans have played an instrumental role in keeping it suitable for life on Earth. Additionally, the oceans lubricate Earth's rocky surface and moderate the climate. It is primarily the planet's internal heat that moves the continent slowly. As on Venus, heat could build up without water and burst out in massive lava flows. Oceans provide an environment where molecules can interact in a liquid medium. Certain conditions can transform mere chemistry into life. A planet with all three ingredients, a solid surface, an atmosphere, and oceans of liquid water, has the potential to create something new. This could be the emergence and evolution of life. Our planet Earth is a shining example of what rocky worlds can do. Earth's wildlife is diverse and complex. Additionally, it has buried its tracks, making it difficult to understand how the planet came to be the way it is today. The technology is now available to explore the rest of the solar system, which is why scientists are so eager to do so. We may find clues about what Earth was like before life appeared, and how the process took place here. Maybe we can only fully comprehend who we are when we reach across the ocean of space to distant, rocky shores. The view of a full moon is perhaps the most haunting and beautiful in all nature. There is something both familiar and mysterious about it. A natural phenomenon. Still, it is unique. Today we find an alter ego in our nearest neighbor, not a mirror image. We have memories of the violent beginnings of our solar system and Earth's turbulent past throughout history. While Earth looks lush and colorful, the moon is a study in black and white. While the Earth's surface is shaped by water and air and is filled with the sounds of life, the moon is silent and still. Neither rivers nor winds blow on the moon. That is all there is. The moon has been Earth's silent partner for billions of years, keeping watch from above and keeping its secrets to itself. Since humans are not very satisfied with that, every civilization in history has a myth about how the moon was created. The story took a fortunate turn with space travel. There have been over 50 spacecraft that have passed by, orbited, or landed on the moon. Viewed up close, the moon's surface is dotted with impact craters. The moon is formed when minor asteroids collide with the surface at high speed. Massive impacts produce enough energy to liquefy and hollow out craters many times the size of the original impactor. The debris will also travel thousands of kilometers. Our planet has taken just as much abuse as the rest of the solar system over billions of years. Earth's impact craters are eroded or buried in sediment. Our solar system's hazardous nature is displayed vividly and precisely on the moon, where they accumulate. The number of craters on the moon can determine which parts of its surface formed first and which later. We can see, for instance, that the dark patches on the moon are younger than the bright areas surrounding them. Maria Latin for seizure was the name given to these dark patches by astronomers in the past. It is clear from up close that there has been no water on these alien shores. Maria is a vast, low-lying plain of volcanic rock, because these plains are richer in iron than other parts of the moon. They were covered with hot lava spilling from the moon's interior. This contrast makes them appear darker. The mapping of both sides of the Moon's surface is a significant accomplishment of lunar exploration. The Moon rotates in sync with its orbital period, with one side facing Earth constantly. This resulted in two different sides. Despite Maria, on the side facing Earth, the far side of the Moon is much less contrasted. The strange sideness of the Moon is because of its crust, which is significantly thicker on the far side. A few more significant impact sites are scattered among the ancient rugged terrain. Researchers now believe that billions of years ago, when the Moon's internal heat forced lava up, it found a shorter route to the surface on its near side. When and how did those circular plains form in the first place? This question is answered by lunar samples returned by the Apollo astronauts. The samples show that the Moon's Maria was once the site of enormous effects, some of which date back approximately between 3 billion to 9 billion years ago. The solar system was more crowded with debris in its history than it is now. A storm of asteroids appears to have swept through the inner solar system, pummeling all the planets and the Moon. It left gigantic circular scars on the Moon and Earth, but it caused far more damage on the Moon. While no animals or plants lived on Earth, the effects would have vaporized oceans and liquefied extensive areas of our planet's crust. Microorganisms may have already appeared. Maybe only those microbes living deep down near deep sea vents survived the bombardment and became our distant ancestors. Astronauts have returned significant samples to Earth after bombarding the Moon and the Earth. Perhaps the biggest surprise is the revelation that the Moon was once the result of a giant collision. A large object as large as Mars collided with Earth early in our solar system's history and caused our planet to suffer a staggering blow. In the first moments after the collision, vast amounts of debris were thrown into orbit around Earth, eventually coalescing to form a single large moon. It may seem incredible, but this giant impact scenario offers the most plausible explanation for some of the Moon's more puzzling characteristics, including its apparent lack of iron core. Because of the Moon's presence, the tilt of the Earth's axis is stabilized, preventing climate swings that would devastate human life and civilization. Ironically, the destructive birth of the Moon may have played a crucial role in maintaining Earth as the cradle of life in our solar system. The Moon's history is closely intertwined with our own because of its formation. Life may have developed differently without the Moon. Without the Moon, we might not even exist. We have gained a fascinating perspective on the past by exploring the Moon. For the US, China, and others, the Moon may also be the gateway to a bright future in space. There are now efforts underway to return humans to the Moon's surface. The goal is ambitious, but it is also a stepping stone to more distant destinations. We still do not know where the next human mission will land. The Moon is not short of exciting places scientists would love to explore. A visit to the lunar South Pole is undoubtedly at the top of their wish list here. The sun never shines on some craters' floors, always in shadow, cold enough for water vapor to condense in these dark craters and even form lunar ice. It is possible that comets colliding with the Moon's surface could cause the water vapor to appear. A recent study found hydrogen in many craters on the South Pole. This is robust evidence of ice. Ice on the Moon could provide explorers with much-needed water, if enough of it. Moon tells us that this world is just one among many in the solar system. It will be a challenge to find and retrieve the ice, since you will have to venture into perpetually dark areas. A new exploration of the Moon could pave the way for even more daring explorations on Mars and beyond in the future. Discoveries beyond the horizon have challenged explorers for generations. Exploring alien worlds with vast new territories is possible thanks to the invention of spaceflight. We may also visit them one day if we are determined enough. Our intrepid machines are blazing a trail across the solar system today, allowing us to observe the Sun, Moon, and planets in unparalleled clarity. Their cameras have become our windows into a bold and exciting world. These discoveries have become our cosmic vistas when everything is strange and exotic. Home is where we belong. When exploring the solar system, Mars is a familiar destination. It is a strange planet. The surface of Mars also has recognizable features. There are deserts and dunes, cliffs and canyons in this world. We can imagine ourselves exploring this landscape firsthand on 2 feet or 6 wheels. Mars is not easier to understand when it is familiar. Mars is better known to us than any other planet in the solar system, except ours. We have studied its landforms from orbit and sampled its soil and rocks from the surface. Its complex history and present state have only increased our questions, including the most important one of all: is there life on this planet? Our journey takes us to the borderland. There is no abundant life on Mars like there is on Earth. As well, there is no chance for life on the Moon. Mars is somewhere in the middle, so we can pinpoint where life is possible and not. The status of Morris Borderland is not revolutionary. More than a century has passed since astronomers first speculated about the possibility of life on Mars. Scientists were surprised and disappointed by the first close-ups of Mars broadcast in 1965. Images of the surface showed it was cratered and barren, much like the Moon. The red planet was the dead planet, and any possibility of finding primitive life on its surface was all but wiped out. It is easy to be deceived by first impressions. After follow-up missions with better cameras began in the late 1960s and early 1970s, it became clear. The planet Mars is more interesting and diverse than anyone ever imagined. Impact craters were present, but there was also evidence of colossal geologic activity. Giant volcanoes were towering over the Martian plains, larger than any on Earth. The largest, Olympus Mons, rises to 24 kilometers, 3 times as high as Mount Everest. Consequently, this is the tallest peak in the solar system and Mars. The impressive structure results from many eruptions of lava that repeatedly flowed across the surface for billions of years. Olympus Mons rises from a giant bulge known as Tharsis, making Mars a lopsided planet. Eventually, it led to a spectacular split in the planet's crust, leading to this gigantic canyon. Its size and scope are unimaginable. It is 10 times bigger than Earth's Grand Canyon, and 4 times more profound. Currently, the most detailed images of Mars come from the Mars Reconnaissance Orbiter, a spacecraft that carries the most powerful telescope ever sent to another world. Mars has never been seen in such detail, allowing us to resolve details on the surface as small as a dinner plate. Mars was once wet, based on the images that suggest water flowed there once. The dunes of Mars are majestic, and there are dust devil tracks left behind. It appears there were layers of sediment in shallow Martian lakes, long before the giant canyon formed deep inside Valles Marineris. Water once flowed on Mars, as evidenced by the shape and orientation of the terrain. As we cast our eyes beyond the Valles Marineris, to a series of significant but empty channels leading from the Tharsis bulge toward the low-lying regions further north, the evidence of watery pasts becomes stronger. Although they have dried up long ago, these valleys were most likely created by vast outflows of moving water that cut across the Martian landscape. The water then spills across the northern plains. Some of these channels are 100 kilometers across and cut through thousands of terrain. Scientists have drastically altered their idea about Mars since they were discovered. These channels bear all the signs of catastrophic flooding and show that water abounds on Mars. Today, Mars is too cold and too thin of an atmosphere for liquid water to survive on its surface. What caused this water to be released, and where did it go? The Tharsis bulge can probably answer the first question. According to some recent research, Mars's giant volcanoes were formed by the intense heat that formed the release of vast quantities of water from its crust. The water initially flowed underground, but it broke through the surface, creating today's features. Other evidence suggests that water flowed on Mars billions of years ago. Observations from orbiting spacecraft suggest that much of this water lies frozen underground as permafrost near the Martian poles. Unlike the rest of Mars, the polar regions of Mars are distinctive. Both the north and south poles of Mars have visible caps of frozen carbon dioxide that expand and contract with the seasons, and both have a smaller underlying cap of water ice that never melts. Additionally, the poles have different surfaces. An abundance of ice mixed in with the rock in these regions, causing cliffs and crater walls to slump, giving them a smooth, rounded appearance. A recent development on Mars is the discovery of gullies running down the sides of craters and canyons. They were formed by groundwater seeping from the cliff faces and running downhill. As small as these features are, they must be recent. If they were older, wind-blown dust would have obscured them? Does liquid water occasionally bubble to the surface of Mars? This would have profound implications for life on Mars. Several decades of exploration have revealed that Mars may have once been home to liquid water and life. Even today, Mars may continue to be an active planet, as evidenced by recent observations. At least geologically, it is not yet a dead world. There is still a borderland there. All of this gives us an impetus to explore Mars further. Like the famous voyages of discovery centuries ago, the journey to another world is fraught with danger. Viewing and sensing from space have their limits. In order to determine whether Mars is a living world, we must touch, taste, and smell it. We can only accomplish these goals by exploring the surface of Mars. Additionally, when it comes to landing on Mars, making a robot that can land itself on Earth is challenging, as humans have never set foot on another planet where they do not know changing conditions. There will be little room for error between a safe landing and a major disaster. In the last 2 minutes and 25 seconds after the entry point, the peril is most dangerous. In addition, to do it in a place so far away, even a simple call for help would take several minutes to reach Earth. That would be a significant challenge. That is precisely what needs to be done to reach another planet. As of now, 6 landers have successfully landed on Mars, and they have transformed our understanding of the planet as only first-hand experience can. Scientifically, these missions have revealed the geologic history of Mars. In addition, these missions have profound global implications. When our probes land on Mars, we are not just looking for the ancient past. A new era in space exploration is dawning, a new beginning. A Viking spacecraft and 2 others became the first to establish a beachhead on Mars 70 years ago. Earth's deserts immediately recalled Earth's geologists. When the Vikings arrived, the similarity disappeared. NASA's Mars Pathfinder landed near the mouth of the Ares Valley, a large channel that appears to be carved by water. Boulders slanting downstream surrounded the landing site. The flood was ancient and violent. It does not entirely rule out life on Mars, but any life that survived here would have had to be sheltered underground or in another inaccessible location. The next successful attempt to land on Mars would not come until 1997. A small rover was the highlight of the mission. It rolled off the lander and trundled up to the nearby rocks to analyze their compositions. A set of wheels was needed to solve the mystery of Mars. Early in 2004, 2 rovers named Spirit and Opportunity landed safely on Mars. Each rover traveled on Mars by motor. From the beginning, the 2 rovers were in very different settings. One was at Gusev crater, the other at Eros crater. As revealed by the orbital evidence, standing water may have left its mark on the soil chemistry from an ancient lake. In the meantime, the Opportunity won a historic victory. Spirit opened its electronic eyes to find a barren plain littered with volcanic rock. The probe was sent to Meridiani Planum, where remote sensing identified hematite, an iron-rich mineral associated with water on Earth. Meridiani initially appeared to be a flat, featureless plain, but a miraculous opportunity landed in a small crater with an exposed rock outcrop. For the first time, scientists will sample rock on Mars where it formed. Everyone found that the opportunity was beyond their wildest expectations as they wheeled up to the outcrop. There was ample evidence that the rock formed in a watery environment because of its layers. As the rock weathered away, hematite was exposed as tiny spheres called blueberries that grew precipitating from the water. Having investigated the terrain near the landing site, scientists sent Spirit rolling toward a set of distant hills nearly 4 kilometers away. The trip to the hills would take 3 months, and climbing them would take even longer. Spirit had finally reached the top when she radioed back a panoramic view. Spirit descended to the other side of the hills during the following years, survived 3 Martian winters, and eventually found the home plate. Those are the remains of a volcanic vent where hot rock once came into contact with water. Meridiani did well as opportunities spread across the plains, uncovering an even more extensive rock outcrop, whose layers read like a geological history book, an ancient tale told of a place that once was wet and acidic, while there was no water at all at other times. We have seen an adventure unlike any other in our exploration of the Red Planet with the Mars rovers. After nearly 2 years, a more roving opportunity arrived at Victoria Crater. and recorded one of the most breathtaking views ever seen on Mars. The newly arrived Mars Reconnaissance Orbiter captured the moment in space, spotting the tiny rover perched at the crater's rim. Water used to flow in places on Mars. Scientists then wanted to know how much water is present on Mars today. They have shown us Mars over many years and kilometers, instead of an isolated spot for a brief time window. Scientists expected to find water locked deep beneath the surface of Mars' polar regions, frozen in a frozen state beneath the surface of the Phoenix lander, which was modest compared to the Mars rovers. Low mounds surrounded by troughs dominate landscapes like this. In these mounds, the soil has been forced upward by the expansion of ground ice. Phoenix discovered something white just centimeters below the surface using its robot arm. Ice proved that Mars used to be wet. In the low-lying northern plains of Mars, where there may once have been a Martian ocean, Phoenix landed. Phoenix could not confirm this, but it found that the soil here is alkaline, similar to seawater here on Earth. All these missions have shown that Mars once was a water world, even though it is hidden from view today. It will be up to future missions to determine for life on Mars. Recent missions have already paved the way for human life on Mars. We may build the leading edge of a fresh wave of exploration that could take astronauts to the Red Planet one day. In that case, the human story on Mars has already begun. The solar system's outer reaches were always cold enough for gas molecules to stick together and form ice. That ice accumulated into ever larger chunks until gravity took over, pulling in vast amounts of material billions of years ago. This set the stage for planet formation on a considerable scale. Cassini's images of Saturn make it one of the best planets imaged in our solar system, despite Saturn's distance from Earth. Saturn continues to amaze and delight us with every new image it takes. You would be better off if you had a spacecraft. With the invention of the telescope, we discovered that there is much more to our solar system than meets the eye. Pluto and Neptune are compelling cases, not Uranus and Neptune. While powerful telescopes can probe the solar system's outer limits, these worlds remain remote and mysterious. It will be the end of an era when New Horizons reveals Pluto. Pluto is no longer officially referred to as a planet, but it represents the last type of object in our solar system that we have not yet seen up close. Discovering what lies beyond the horizon has challenged explorers for generations. Because of the invention of spaceflight, we are now discovering alien worlds with vast new territories. With the help of intrepid machines blazing a trail across the solar system, we see the sun, moon, and planets with penetrating clarity today. Their cameras have been our windows on an adventurous and daring journey. In our solar system, there are over 100 moons. Almost all of them orbit Jupiter and Saturn, the two most important planets. Jupiter has many moons orbiting it. Collectively, they range from small to large, cold to hot, and quiet to active. There may be a hidden haven for alien life somewhere in that range of possibilities. Saturn is reasonably small, but some of its moons are so large and complex they could easily qualify as planets. Over the past 300 years, astronomers had little to say about these fascinating places thanks to spaceflight. However, that has changed. In 1979, Voyager and 2 flew past Jupiter's 4 largest moons with their cameras rolling. Radioed pictures reveal that each moon has a unique personality and features never seen before. Io, the innermost of the 4 moons, was the most surprising. Unlike our moon, its surface is mottled and sulphurous. Its surface is devoid of craters. The craters seem to be erased by a mysterious agent. Voyager 1 spotted something unusual, protruding 300 kilometers from one side of Io. A giant volcano erupted in a fountain of ash. Since then, it has become apparent that Io is the most geologically active planet in the solar system. The surface of Io is one giant larger flow, with more than a dozen active volcanoes towering over the sulfur-rich landscape. Io generates vast amounts of heat because of the tug-of-war between Jupiter and some of its other large moons. This results in a dynamic surface, but it is inhospitable to life. Callisto, Jupiter's outermost large moon, could not be more different. Callisto's battered face is dotted with ancient impact craters, suggesting that little has happened here since it formed. It is easy to be deceived by appearances. Ganymede, Our largest moon, and one of the most peculiar looking in our solar system, shows signs of a geologically active past. Recent data suggests there might be salty water beneath Callisto's surface of ice and rock. The survival of life in such an environment remains an open question. A dark and heavily cratered area of Callisto. Unlike the dark areas, the parallel grooves and ridges of the more recent terrain break up the dark areas. Exactly how these ridges and grooves form remains a mystery. Ganymede also has a warmer interior than Callisto. Ganymede's interior may have once been heated, causing parts of its surface to drift apart as on Earth. The heat likely caused Ganymede's interior to separate into layers, starting with an iron-rich core at its center, a rock mantle surrounding it, and a layer of ice on top. On Ganymede, there is evidence of an ocean of salt water below the surface, as there was on Callisto. Ganymede may finally maintain life with the right combination of heat and water. However, life forms such as these would be isolated from the Sun. Ganymede has an ocean beneath its frozen surface, 200 kilometers deep. It might survive on chemical energy, like deep-sea creatures around Earth's ocean vents. That possibility will not be tested for a time. There may be a better opportunity in Europa to explore the ocean of another world. Europa appears to be the least interesting of Jupiter's moons because of its flat, smooth surface. A lack of dramatic relief, like large craters or mountains, might show nearby water. Cracks crisscross Europa's ice crust, occasionally breaking open, letting slushy water spill out. Scientists found what appeared to be icebergs floating apart in one area before the surface reef froze. Europa's ocean is on the top of the list of locations where scientists are eager to search for alien life today. The surface ice of Europa has some cracks that are darker and redder than the rest. The ocean beneath could be rich in sulfur compounds and organic molecules. There is some sign that this ocean may be closer to the surface than 10 kilometers in some places. The possibility of drilling down and exploring another planet's marine environment may be within reach in the future. I expect many mysteries to be hidden on the moons of Jupiter. Titan was shrouded in a thick orange haze when Voyager 1 arrived in 1980. Titan, Saturn's giant moon, is hidden even from view on its surface. Our solar system's only moon with a substantial atmosphere is Titan. Titan's atmosphere produces a haze similar to the photochemical smog when sunlight reacts with methane. Scientists would have to wait for an entire generation before revisiting Titan. When Cassini landed at Saturn in 2004, it used a high-powered camera equipped with an infrared filter to peer through Titan's thick haze. Cassini found a surface divided into mysterious light and dark regions resembling ancient coastlines. Titan has also been detected by Cassini, confirming that the moon's surface is solid and has unusual landforms like ice, volcanoes, and wind-blown dunes. Cassini's radar made a further discovery after several more passes of Titan. There were a series of dark patches that were perfectly flat, resembling the surfaces of small lakes, prompting scientists to search for more direct evidence of fluid flow on Titan. Cassini's probe descended slowly into Titan's cloudy atmosphere after deploying its parachute. Images were transmitted to Cassini. As soon as it emerged from the clouds, the probe saw exciting details, as if the liquid had carved them. Finally, the probe survived its impact and sent back a spectacular image. On Earth, rocks in a stream bed are surrounded by a fluid flow, like chunks of ice on the planet's surface. Since Titan is so cold, water is like rock, but methane, a gas on Earth, can rain down from Titan's atmosphere and flow like liquid over its surface. It is a component of the kinds of complex molecules that led to the emergence of life on Earth. In addition, if Titan has an internal heat source, like some of Jupiter's moons, it could harbor its ecosystem deep below the surface. In our exploration of the outer solar system, Titan and Jupiter's moons have become more than just sideshows to the planets they orbit. Water appears to be a given on Earth. 70% of Earth's surface is covered by water, and its presence is essential to life on the planet. Water plays a different role in the dim reaches of Saturn's outer solar system. In these regions, temperatures are near 100 degrees Celsius, and water is everywhere. Water cannot exist in a liquid state. It is so solid that it remains frozen, even though it covers planets. The world depends on it. At Saturn, ice is the primary ingredient in forming moons. Cassini has revealed spectacular details about Saturn's moons, surrounded by an entire family of icy moons. Scientists hope that exploring these frozen worlds will reveal an ancient story about Saturn and the entire outer solar system. Phoebe is undoubtedly the first moon Cassini encountered up close, as it was the first of Saturn's moons. Phoebe is too small and its gravity too weak to pull itself into a sphere just 200 kilometers in diameter. Phoebe was found to have a carbon-rich surface with deep craters that exposed layers of bright white ice below. Phoebe is darker and contains more rock than Saturn's other icy moons. It did not originate near Saturn, but in the Kuiper Belt beyond Neptune. This zone contains ancient objects. These are the original building blocks of our solar system. Phoebe escaped from that region and was later captured by Saturn and transformed into a moon. Observing this moon gives us a glimpse of what we will find at a great distance from the Sun. Besides being 4 times closer to Saturn than Phoebe, Iapetus is also 4 times larger. Although it is 80% ice, its most distinctive feature is its two-tone shading. Iapetus has a black side and a whitish-grey side. It is also significantly more remarkable on the black side. This difference equates to about 15 degrees warmer on the dark side. Scientists now believe that dark material may have fallen long ago onto Iapetus from the surface of Phoebe. Dust received more of the sun's energy on the side that received it. There, the ice sublimated, leaving behind grains of dust and rock that darkened the surface further. In the meantime, the vaporized ice resettled on the other side of the Iapetus and around its poles, creating the appearance it has today. Cassini discovered running along Iapetus's equator, thanks to a long ridge, that it looks like a walnut. The ridge rises to 13 kilometers in space. We do not know what created this bizarre feature. It probably happened when Iapetus spun faster and had more internal heat shaping its surface. Hyperion, an irregular honeycombed object with an odd shape, moves closer to Saturn. The shape and appearance of Hyperion suggest it is the remnant of a giant moon that shattered in a collision. Perhaps it is not even solid, but a loosely packed pile of rubble. Cassini's measurements reveal Hyperion has over 40% of its mass in space. There are signs of ancient collisions on Saturn's moons, including Rhea, Dione, and Tethys. At first glance, these 3 round moons seem to be identical triplets. The two are over 1,000 kilometers across and covered in craters from billions of years ago. Each is a variation of the other. There are distinct characteristics among the 3, suggesting a more complex and diverse past. Kuzma, for instance, wraps around Tethys like a waistband in Ithaca, a vast canyon. Tethys may have formed this long ago when its icy interior froze and expanded, causing its crust to stretch apart at its seams. Scientists observed a series of wispy white lines running across Dione's surface from afar long ago. Cassini revealed the lines of the bright faces of cliffs formed when internal forces repeatedly shattered Dione. Rhea presented Cassini with indirect evidence that this moon was surrounded by a dark, dusty ring, making it the only moon anywhere in the solar system with its ring. At least one of Saturn's icy moons may have once been geologically active, but subsequently cooled and grew dormant. This has enormous implications. In addition, Enceladus has a diameter of 500 kilometers. This object size is usually too small to sustain heat for billions of years. Enceladus is not like other planets. Cassini's investigations of the surface have revealed a strange and puzzling sight. Cassini spotted a considerable water vapor geyser near the south pole of Saturn. During Enceladus's orbit around Saturn, the vapor carries dust grains, which escape into space and form a diffuse ring. In addition, Enceladus is stricken with long, deep gouges nicknamed tiger stripes, from which the geysers are said to arise. Stripes surround fresh eyes. This suggests that temperatures below the surface are sufficiently high to melt ice and hold liquid water under pressure before venting into space like a tea kettle. Enceladus is at the edge of our solar system's icy region. The exact mechanism by which Enceladus does this is unknown. According to Cassini, Saturn's moon, Enceladus, has more rock and metal than many of Saturn's other moons. Saturn and its moons produce powerful tides, so it is warmed by a combination of radioactive heating from within and tides from Saturn. Of even greater interest are the organic molecules within the tiger stripes. Enceladus has all the ingredients for life if liquid water is present. This is an astonishing discovery. The icy moons of Saturn are strange. Science's goal is to learn how these strange worlds formed and developed, despite their utter differences from Earth. Why, you ask? There must be countless icy moons in the universe, if there are so many in our solar system. There is at least the potential for life whenever one of those moons gets warm enough to melt the ice into water. Perhaps this is our best shot at answering the age-old question, is there anyone else out there? For centuries, astronomers have thought of the solar system as an orderly place where planets, including Earth, go about their daily lives in peace. Today, we realize that the solar system is a cosmic shooting gallery filled with asteroids and comets that could threaten life on Earth. Exploring these objects is therefore not simply a matter of science, but survival as well. This is an ironic result. The danger posed by comets and asteroids to life on Earth is part of what motivates our interest in them. There is a strong possibility that life on Earth would not exist without comets and asteroids. The discovery that the Sun is just one star among billions, and Earth just one planet, led astronomers to assume that there are other worlds beyond our solar system. It took nearly 4 centuries since the invention of the telescope for us to find these worlds, which is a technical challenge of the highest order. We have seen a revolution in our ability to discover and study planets beyond our solar system in the last 15 years. The following 15 years will be even more exciting as Kepler and its successors attempt to find planets like Earth. Once they find such planets, they will look for evidence of life.
42,000 years ago, unusual events occurred on Earth. About 42,000 years ago, the Earth experienced a significant historical turning point. Unusual electrical storms and extensive auroras occurred alongside an increase in cosmic radiation. The catastrophic climate changes and mass extinctions were caused by a transient change in the Earth's magnetic field. A planet's magnetic field is one of the most significant determinants of its fate. As with Mars, a lack of magnetic field can render a planet desolate. It can even determine whether a person lives or dies. The Earth's magnetic field shields us from cosmic radiation and solar-emitted charged particles. Consequently, a sudden change in the strength of the magnetic field could inflict havoc on Earth, and a similar event occurred in the recent past. But what precisely occurred 42,000 years ago? How did scientists uncover the change that occurred in the magnetic field in the past? Will a similar event occur soon? Let's examine the origin of the magnetic field on Earth. It is known that most planets in the solar system generate magnetic fields because of the movement of electricity-conducting fluids within them. And the same holds true for our planet. In terms of the inner structure of the Earth, there's a 3,400-kilometer-long region of iron alloys. It comprises a solid interior core with a radius of 1,220 kilometers and a liquid outer core. As the planet rotates, the rolling of molten metal around the planet's iron core generates electricity that produces magnetic field lines. These lines curve from pole to pole around the planet to create the magnetosphere. The magnetic field of the planet functions as a natural protection. It provides protection against hazardous solar radiation. On the side facing the sun, the incessant bombardment of solar wind compresses the magnetic field. Consequently, the field on this side extends to a distance no greater than 10 times the radius of the Earth, whereas it extends further into space on the opposite side, facing away from the sun. The two locations formed an arch. As a result, magnetic field lines converge at the magnetic North Pole and the magnetic South Pole. Although these positions are comparatively stable, the magnetic poles and magnetic fields are not fixed because of the constantly changing forces. The field intensity fluctuates. It becomes weak enough every 200,000 to 300,000 years to completely reverse the polarity. It is believed that this magnetic field reversal occurred between 41,000 and 42,000 years ago. This event is referred to as the cosmic bubble. Our solar system is in the middle of a mostly vacant region of space. This cavity has a particle density at least 10 times lower than the average density of our galaxy's interstellar medium. In addition, it contains a thin group of X-ray emitting plasma with temperatures that can reach 1 million degrees. This cavity is the local sphere, where our Sun and thousands of nearby stars reside. However, how did we find this bubble? How did it initially originate? When did the Sun penetrate it? First, the local bubble is not spherical, so calling it a bubble is inaccurate. Instead, it appears to have an hourglass shape, narrowest in the galactic plane and expanding above and below it. In addition, the bubble appears to have no end and explodes into the galactic halo in a direction away from the galactic plane. It has a diameter of approximately 1,000 light-years and is enveloped by colder, denser, neutral gas and dust. Several cloudlets of the interstellar medium and cosmic bodies are aligned in sheet-like structures near the bubble's boundary, along with several neighboring stars within this vacuum. Currently, the Sun is enveloped by a cluster of cloudlets known as the local fuzz complex. Then, some passages branch off the local bubble through the surrounding dense gas and lead to the opening of additional cavities. These interconnected cavities and tunnels are comparable to the pores in a typical sponge. Using a combination of optical, radio, and X-ray astronomy, the local bubble was discovered between the 1970s and 1980s. However, for years it was unknown how such a structure initially formed in a typical sponge. As a result, different missions have been undertaken to study the bubble's anatomy over the years. First, the Extreme Ultraviolet Explorer mission, which ran from 1992 to 2001 and investigated hot EUV sources within the bubble, considered it a region of particular interest. Then, in February of 2003, the Cosmic Hot Interstellar Plasma Spectrometer CHIPS, or CHIPSAT, was launched. This mission lasted until 2008 and investigated the heated gas within the local bubble. The most significant achievement in studying this cosmic void occurred in 2019, when researchers published the first 3D depiction of the local bubble based on observations of diffuse interstellar bands. A precise map was drawn with the data published by Gaia. Gaia is an ongoing initiative that seeks to precisely map the position and motion of stars in the Milky Way. The mission may not be as well known as the Hubble Space Telescope or the James Webb Space Telescope, but its data has significantly contributed to our comprehension of the Milky Way. Gas and immature stars within 650 light-years of the Sun are also mapped by Gaia. Largest known galaxy. Astronomers have found the largest known galaxy to date, and it is so large that it'll shatter your cranium. It is a radio galaxy located 3 billion light-years away in the constellation Lynx. This means it takes 3 billion years of this galaxy's 300,000 kilometers per second of light to reach us. This enormous galaxy, designated Alcyoneus, has perplexed astronomers. What is a radio galaxy, though, and does it differ from the galaxy in which we reside? Moreover, how large is it compared to the Milky Way? A century ago, our exploration of galaxies was a fascinating endeavor. We believe that the Milky Way is the only galaxy in the universe. We had images of other galaxies, such as the Andromeda Galaxy. However, astronomers believe they are star systems within the Milky Way. After a century, the number has increased to 2 trillion. In the universe, astronomers have observed a diversity of galaxies: spiral, elliptical, irregular, lenticular, asymmetrical, interacting, and merging galaxies exist. However, this is merely a clear classification based on what we observe with a telescope in the visible region of the electromagnetic spectrum. Objects in our universe emanate energy over a broad range of frequencies, and their luminosity in various portions of the electromagnetic spectrum varies depending on the energy they emit. This means an extremely dim object in the visible spectrum can appear extremely bright in radio or infrared radiation. Alcyonus is one of the radio galaxies which are extremely bright at radio wavelengths. Now the query is, what distinguishes radio galaxies from others? What additional information do we gain from radio frequency exploration of the sky? Because of the longer wavelengths of radio waves, radio emissions are one of the finest methods for decoding the mysteries of the universe. They can also travel through dense dust clouds, providing unobstructed views of the cosmos that are otherwise invisible in the optical spectrum. There are various emission mechanics by which radio waves are emitted by astrophysical objects. However, the most prevalent emission mechanism is the phenomenon of synchrotron emission, and most radio galaxies emit radio frequencies because of this phenomenon. What exactly is that? Surely you learned about cyclotron radiation in high school physics class. When electrons in a cyclotron with a circular orbit are sped up in a magnetic field, they emit radiation proportional to their cyclotron frequency. As electrons travel at relativistic velocities, synchrotron radiation is merely the relativistic counterpart of cyclotron radiation. As in other galaxies, synchrotron emission is one of the most potent and dominant radio emission mechanisms. Radio galaxies comprise a host galaxy of stars in orbit around a galactic nucleus containing a supermassive black hole. This is accompanied by gigantic jets and lobes emanating from the galaxy's center. These jets and lobes interact with the intergalactic medium and ultimately operate as a synchrotron to speed up electrons that emit radio waves. This is a common occurrence. Even the Milky Way has radio lobes. In some galaxies, however, the radio lobes expand to dimensions of megaparsecs. Consequently, these galaxies are Triton's strange characteristics. Despite its unique characteristics, Triton needs to be more frequently addressed. Many of its characteristics are singular. Consequently, it is among the most fascinating objects in our solar system. Despite being the largest moon of Neptune, it is the planet's most distant neighbor. Because of this, we have only visited it once, briefly in 1989, 30 years ago. How has it changed, and what has it revealed since the last visit? First, discuss Triton's position in the solar system and the local ecosystem. There are 14 known moons of Neptune, including Triton. 7 moons orbit Neptune's ecliptic in circular paths with extremely low eccentricities. After these regular interior moons, Triton is the first irregular moon. The orbits of irregularly orbiting moons are inclined, eccentric, and frequently retrograde. Triton's spherical structure distinguishes it from other spherical moons in the solar system. The planet's orbit is irregular. As Triton orbits anti-clockwise around Neptune, an angle of 130 degrees is formed between Triton's orbit and Neptune's ecliptic. Even though its eccentricity is close to zero, its orbital eccentricity merits consideration. In its orbit, circularity is almost ideal. Other large moons in our solar system orbit their parent planets in the same direction. This shows that Triton was not formed alongside Neptune, but as an object captured by Neptune, specifically a dwarf planet. This moon comprises 99.5% of Neptune's orbital mass, making it the largest of Neptune's 14 moons. What is the proportion of that? Despite being smaller than the Earth's moon, it is the second largest moon on its progenitor planet. Because of its close orbit around Neptune, it appears roughly the same magnitude as our moon in the sky. Despite being the 7th largest moon in the solar system, it is significantly more significant than Pluto. Since Triton once governed this region before Neptune captured it, Pluto may appear to be the Kuiper Belt's king. Because being Neptune's moon, Triton is the largest object in the Kuiper Belt. In 2015, New Horizons flew by Pluto and discovered that Triton and Pluto share a vertically identical composition, supporting the theory that they originated from the same planet. Additionally, 6 additional irregular moons were found beyond Triton, almost certainly objects with unusually eccentric orbits that take years to complete are captured. The Triton's gravity may have perturbed their orbits. Consequently, how was Triton captured? To capture an object, one must sacrifice speed. They could then escape if they had sufficient momentum. According to the most widely accepted theory, Triton was once a member of a binary system, like Pluto and Charon. As Neptune approached, Triton's moon would have been propelled away by Neptune's gravity. causing Triton to lose momentum and orbit Neptune. As previously mentioned, Triton and Pluto share similar qualities. What does that mean precisely? They also contain water ice, carbon dioxide ice, and nitrogen ice. There are multiple levels of regions there. The maximum difference in topography is 1 kilometer. Voyager 2 did, however, observe plateaus, ridges, and icy plains. Although it may startle you, it has very few craters. Consequently, its surface is perpetually renewed, as is Pluto's. Besides the reddish regions, methane reacted with ultraviolet light to produce tholins, and organic compounds resembling tar. Organic compounds do not inevitably support life. Life cannot exist on Triton's surface, as the temperature is too low and the sun is too faint to support life. Under Triton's crust, like Titan's surface, is believed to be a stony and metallic interior, giving Triton a relatively high density for a moon of 2 grams per centimeter cubed. This is because the moon is significantly larger than the next largest moon in the solar system. Titan has a greater mass than all of the lesser moons combined in the solar system. Like the subsurface oceans on Europa, Enceladus, and other large moons in our solar system, radioactive decay from the rocky core could heat and fuel convection in a subsurface ocean. Cryovolcanism is a dynamic phenomenon similar to Europa and Enceladus. On Triton, as on Earth, liquid water erupts from the mantle today. The surface is so youthful. The surface of Triton has been actively renewed by the eruption and cooling of liquid water. Young, sparse, and relatively level lava plains surrounded by an intriguing wall have been discovered. The lake of solidified magma is known as Planitia. Also visible is the caldera that formed at the center of the cryovolcanoes. These eruptions brought minerals from the subterranean oceans, possibly even tholins and organic matter, to the surface. If this is the case, the subsurface ocean may contain organic compounds. Life could have formed there, had the conditions been favorable. Additionally, lengthy lines permeate the surface. These faults are most likely caused by tectonic activity or freeze-thaw degradation. Recent eruptions are visible in some Triton images captured by Voyager 2. Up to 150 kilometers long, surface deposits resemble cones or funnels. The mantle may not be accountable for these minor eruptions. During Voyager 2, the spacecraft detected 8-kilometer tall plumes, believed to result from a significant greenhouse effect within the moon's ice crust. Assume that Triton's surface is composed of clear ice deposited on opaque deposits such as tholins. The sun's rays penetrate the ice, warming the darker, more absorbent tholins beneath, which are ice pockets. The pressure created by the sublimination of the ice in the air pocket causes the surface above the air pocket to collapse, resulting in an eruption. Besides distributing the dark deposits across the surface, this eruption also transports the dark deposits. Under the polar ice cap on Mars, carbon dioxide ice and dark deposits have been observed. If this is the case, one factor makes this procedure workable. Researchers initially expected that Triton's atmosphere would be denser. However, approximately 80 kilometers above the surface of the Earth, Triton's atmosphere is only 0.014 millibars dense. However, this density varies seasonally, similar to Pluto's. Since Voyager 2 observed Triton's atmosphere becoming denser as the surface warmed, some of the nitrogen ice on the planet's surface has evaporated. Despite this, Triton's atmosphere was still dense enough to sustain weather 8 kilometers above the planet's surface when Voyager 2 passed. As a result, there are clouds visible on Triton in this image. As seen in the image of the plumes, the predominant wind in that region has caused all eruptive deposits to face the same direction. The hazy atmosphere of Triton is believed to be caused by hydrocarbons that have not yet been broken down by sunlight into tholins. Seasonal variations cause the evaporation and refreeze of ice, while cryovolcanism deposits organic compounds continuously. Rich weather and a lively ambiance make Triton an extremely dynamic place. Pluto is the most well-known moon in the Kuiper Belt, but it is a dwarf planet rather than a moon. These factors combine to make it an uncommon moon. The nearest black hole. Astronomers have made a groundbreaking discovery by locating the black hole nearest our solar system. It is part of a binary system with a star similar to the Sun orbiting it. Initially, astronomers believed it to be a typical binary system comprising two celestial objects. However, when they examined the star's properties and how it orbits the black hole, they immediately realized something unusual was occurring. They had never observed a black hole or star in such a binary system. This discovery has led us to an altogether new astronomical concept we were unaware of. How did astronomers discover this? First, a black hole exists in that system. What makes the closest black hole we've discovered so special? Most significantly, what contribution has this discovery made to physics and astronomy? Regarding this discovery, astronomers utilize Gaia mission data. Gaia contributes silently to the field of astronomy. It is less prominent than the Hubble telescope or the James Webb Space Telescope. However, Gaia's extensive sky surveys have altered the trajectory of astronomy over the past few years, though only some are aware of this. It is a European Space Agency space observatory that was launched in 2013. Gaia constructs a three-dimensional map of the Milky Way using astronomy, which entails precisely determining the locations, speeds, and trajectories of stars and other astronomical objects to comprehend their origin and future in our galaxy. Gaia shares the L2 Lagrange point with the James Webb Telescope as it orbits the Sun 1 million miles from Earth. Since its inception, 3 datasets have been released by the observatory. The most recent one was in 2022. Gaia has revolutionized astronomy through these datasets, as many research papers are published daily based on them. For example, Gaia discovered a binary system comprising a solar-like star and a black hole in its third data transmission. Informal usage refers to the sources as Gaia BH1. The binary system is approximately 1,500 light-years away from Earth. It comprises a black hole with 10 times more massive stellar mass than the Sun and the G-type main sequence star with solar mass. Based on their surface temperatures, stars are classified into 7 primary spectral classes in stellar astrophysics: M, O, B, A, F, G, and K. The surface temperatures of O-type stars exceed 30,000 Kelvin, while those of M-type stars range between 2400 and 3700 Kelvin. This order can be remembered using a classic mnemonic: "Oh, be a lovely woman, kiss me." According to this classification, a G-type star, like our Sun, would have a temperature between 5200 and 6000 Kelvin. Consequently, astronomers determined that the star in the Gaia BH1 system is a G-type star, with a surface temperature of approximately 5850 Kelvin, near the Sun's temperature of 5778 Kelvin. Because its mass is equivalent to the Sun's, the star is not identical like the Sun. Astronomers also found it peculiar that there was no significant mass transfer between the black hole and the G-star. Consequently, it is a dormant black hole that emits no X-ray radiation, making it even harder to detect. This brings us to the following inquiry: how did astronomers determine that the central object of the system is a black hole? It could be a dense neutron star or a white dwarf, which are challenging to detect because of their own luminosity. The answer resides in the star's orbit. Observing the star's motion in orbit because of a dark object's gravitational pull, astronomers deduce 2 intriguing facts about the binary system. First, the orbital configuration and orbital period. Consider this example from the research paper. The left quadrant depicts the predicted motion of the G-star in the sky over the next 6 years. After subtracting parallax and proper motion, the middle panel depicts the star's motion about its mass center, or barycenter. The final panel depicts the star's trajectory based solely on Gaia's astrometric solution. Its orbit around the unseen companion is mathematically elliptical and highly eccentric. Eccentricity gauges the deviation of an orbit from a perfect circle. Its value for the G-star is 0.45, twice that of Pluto's solar system orbit. The star's elliptical orbit revealed 185.6 days. Using these data, scientists calculated that the mass of the central dark object is roughly 10 times that of the Sun. The same calculation would hold true for 2 black holes with lesser masses, 5 neutron stars, 10 white dwarf stars, or 200 brown dwarfs at the center. The solution lies in dynamic stability. The presence of over 2 objects within the orbit of the G-star would render the system dynamically unstable. So it was determined that the unknown companion is a single stellar mass black hole or two compact objects, with black holes being the more likely possibility. The wobble is another intriguing aspect of the G-star's eccentric orbit. Only dark companions with the same mass as the bright object could generate such mass oscillation. Thus, the existence of a black hole was shown. However, this is where things become peculiar. The recently discovered binary system was atypical or unusual. Compare this graph between the black hole's mass and the star's orbital period within the system to known binary black hole systems. Gaia BH1 is distinguishable. Its characteristics resemble NGC 3201, a globular cluster with a distinct evolution channel, making their comparison irrelevant, and this is a major issue. Why? Because of its isolation from other binary systems, no stranded paradigm of binary evolution could adequately explain the origin and properties of this system. As with any significant scientific discovery, this raises some intriguing concerns. Astronomers have developed theories to explain the evolution of the system. The initial model is the stranded envelope evolution model. The mass of the black hole is 10 times that of the Sun. Therefore, its progenitor, the star that collapsed into this black hole, must have been larger than the current orbit of the star. This shows that the G-type star may have been engulfed in the progenitor's gas envelope, spiraled through it, and eventually expelled. This hypothesis sounds intriguing, but it is improbable that a star of solar mass could have discharged the gas envelope of a black hole progenitor with a high mass. Also, the extent of the star's orbit is much larger than the stranded envelope model predicted. Existing binary evolution models are also plagued by similar difficulties. The system may have formed dynamically in an open star cluster that disintegrated. However, the triple star system paradigm best explains the system's evolution. According to this hypothesis, the G-star was initially a tertiary companion to a close binary system composed of two massive stars. Their interaction prevented them from becoming red supergiants, eventually forming a two lower mass black hole binary system with a tertiary G-star companion orbiting in a slightly more compact orbit. If the system is a binary with a G-star and one black hole in the future, the G-star will become a red giant, resulting in the black hole accreting mass, and the system will become a binary system composed of a white dwarf and a black hole. However, suppose it is a triple object system composed of an inner binary of two black holes, and an external binary with a G-type star as the third component. In such a case, the merger of black holes may disrupt the evolution, causing the external binary to disintegrate. The discovery of the closest black hole with unique properties suggests our galaxy contains many binary systems containing quiescent black holes. Gaia's future data releases will facilitate the discovery of many additional quiescent black holes. An unknown universal force. The fifth fundamental force in nature, which physicists have sought for decades, may have just been discovered. However, how do we know that an additional force exists, and why is it necessary in physics? Everything visible in the universe is governed by four well-known fundamental forces. First is gravity, which causes the planets to orbit the Sun. It governs the motion of celestial objects and is the weakest force in nature. Gravity governs everything, from colliding galaxies to merging black holes, to satellites, moons, and planets in orbit. The electromagnetic force that governs the motion of an electron around an atomic nucleus is the second force. In addition, the electromagnetic force is the force that controls the behavior of light. Light consists solely of an electromagnetic wave propagating through space. The weak nuclear force handles the radioactive decay of nuclei. The ultimate force is the strong nuclear force, which holds the protons and neutrons within the nucleus together. As its name suggests, it is nature's most powerful force. So far, so fine. To comprehend the origin of an additional force, we must return to the 1950s. The age of particle discoveries had arrived. Several novel particles are discovered each year. There was a quip among physicists that the Nobel Prize for the year must go to someone who did not discover any new particles. Experimentalists were ecstatic, but theoretical physicists were drowning in a sea of new particles, so they had to devise a plausible classification and explanation for the particles. Moreover, it predicts the existence of new species. Such a theory took more than a decade to develop. This theory is that standard paradigm for unifying three of the four fundamental forces in physics. Gravity is not involved. Einstein's general theory of relativity defines gravity more precisely. It is essential to comprehend the standard model to comprehend the so-called fifth fundamental force. The table of the standard model comprises four types of particles. The first family comprises 6 particles. Hadrons are composed of the fundamental particles protons and neutrons. Following are 6 leptons, electron, muon, tau, and the 3 neutrinos. The 4 gauge bosons, or force carriers, are the photon, gluon, W, and Z. The Higgs boson, the last missing element of the standard model discovered in the previous decade, has been discovered. Although a masterpiece is incomplete, the conventional paradigm of physics cannot reconcile gravity with other forces, and does not mention dark matter and dark energy, which account for approximately 96% of the observable universe. Therefore, physicists have spent decades searching for a new natural force. Analyzing the decay of the beauty quark makes it possible to locate this fundamental force in the quark family. An unstable particle decays into other particles in less than 1.5 quadrillionths of a second. Under the influence of the weak force, a quark decays into a collection of lesser particles, including electrons. An additional force of nature may manifest itself by subtly altering the rate at which quarks decay into other categories of particles. According to the standard model, a decaying quark should not be able to distinguish between an electron and a muon. A muon is identical to an electron except it is 200 times heavier. Therefore, the decay rate of the beauty quark into a muon must be identical to that of the electron. In March 2021, however, researchers determined muon decay occurred only 85% as frequently as electron decay. Nature favors one degradation pathway over another, a violation of the universality law of leptons. As exciting as it was to witness this anomaly, there was a 1 in 1,000 chance that the result was a statistical accident because of a random statistical fluctuation. Scientists refer to this value as 3 sigma. To be confident in a discovery or observation, we must achieve 5 sigma, which corresponds to less than a 1 in 1 million possibilities that the effect is because of a statistical fluke. Currently, researchers are analyzing additional LHCb experiment data. The B in LHCb represents attractiveness. However, attractiveness has yet to be studied by scientists, since all quarks are bound to form larger particles. Quarks decay directly. The March study examined the combination of beauty quarks and up quarks. The new findings investigated 2 decays, one in which the beauty quarks were paired with down quarks, and another in which they were paired with up quarks. It should not matter that the pairing is distinct because the decay occurring beneath the surface is identical. Scientists expect to observe the same effect if there is an unknown force, precisely what they observed this time. Muon decays occur approximately 70% as frequently as electron decays, but with a substantial error, so the result is approximately 2 sigma from the standard model. Approximately a 2% chance of being a statistical anomaly, but not precise enough to be conclusive evidence of an unknown force. This shows that the new study aligns precisely with the previous result and supports the notion that a significant breakthrough may occur. In the meantime, additional investigations at the LHC and the Bell, 2 Japanese investigations, are approaching the same measurements. Exciting because this research may shed light on the universe's most fundamental constituents. Dark energy enigmas. Dark energy could be produced by black holes. New research suggests that supermassive black holes may be the source of dark energy, one of the universe's most enigmatic entities. According to our most successful cosmological model, 68% of the universe comprises dark energy, while only 5% comprises conventional matter, such as stars and galaxies. Despite having similar names, dark energy and dark matter are distinct entities whose compositions remain a mystery to scientists. Comprehending whatever makes up dark energy is crucial because it determines the entire universe's fate. However, the problem is that, although it is an intriguing idea, only some people are receptive. How did astronomers conclude this? What observations of the universe led them to this conclusion? Most significantly, why is this concept so controversial? The first sign of the relationship between dark energy and black holes did not originate from either. Instead, it came from elliptical galaxies. These galaxies have an ellipsoidal shape and lack the spiral arms typical of their spiral counterparts. Their star populations are typically older and redder. Elliptical galaxies are believed to be in the final phases of galaxy evolution. Future collisions and mergers of spiral galaxies or the gravitational collapse of interstellar gas clouds will probably produce them. For example, it is hypothesized that when the Milky Way collides with the Andromeda Galaxy, its spiral structures will transform into an elliptical galaxy. Despite their diverse origins, all elliptical galaxies observed lack the gas and dust required for conventional star formation. This deficiency is attributed to a supermassive black hole at the galaxy's center, which accretes mass from the surrounding stars, limiting their development and eventually depleting the fuel required for star formation. Consequently, the black hole ceases to accrete, resulting in a galaxy devoid of new stars. This relationship between supermassive black holes and the termination of star formation in elliptical galaxies is essential for comprehending the relationship between black holes and dark energy. Once formed, elliptical galaxies are stable in mass and shape. However, recent research shows that the mass of some elliptical galaxies increases over time, prompting astrophysicist Duncan Farah and his colleagues to investigate the evolution of these galaxies in greater detail. Their research focused on elliptical galaxies of varying ages whose nuclei contained millions or billions of times more massive supermassive black holes than the Sun. When drawing galaxy maps, the team observed a perplexing trend about their black hole and stellar mass in this graph. The crimson dots represent old ellipticals in the vicinity. Blue dots represent ellipticals from 6 billion years ago, while orange dots represent ellipticals from the first 2 to 3 billion years of existence. Astronomers have compared the same juvenile elliptical galaxies that emerged in the early universe to the old elliptical galaxies we observe in our local universe. By comparing them, astronomers can study the transformation of juvenile galaxies into the galaxies we observe today. However, the correlation between the mass of the stars in the galaxy and the mass of the supermassive black hole was significantly off. Black holes at the nuclei of low redshift elliptical galaxies had masses 7 to 20 times greater than predicted by research on galaxies with high redshift. This unanticipated discovery challenges our current understanding of the evolution of galaxies. Where is the extra mass coming from if ellipticals are stable once entirely formed? This query may be answered by dark energy. However, to comprehend how dark energy may be related to the excess mass of black holes in elliptical galaxies, it's necessary to investigate two essential concepts: vacuum energy and cosmological coupling. The energy that pervades all of space and time is called vacuum energy. This energy results from the constant emergence of virtual particles within the constraints of the energy-time uncertainty principle. The total energy of vacuum fluctuations is relatively constant despite the apparent randomness of this process. The interior space, or vacuum, also expands as the universe expands, increasing the total vacuum energy. The new model suggests black holes have an expanding energy deficit within their interiors. Consequently, the black hole's energy increases. According to Einstein's mass-energy equivalence, the black hole's mass must increase as energy increases. However, the black hole exerts negative pressure outward to conserve the universe's energy. This negative pressure speeds up the universe's expansion by pushing everything around the black hole away from it. The precise nature of dark energy is the negative pressure exerted by the black hole. According to the equation of state, the energy density of dark energy is equivalent to the negative pressure it exerts. This implies that dark energy and black holes are cosmologically coupled or interconnected. A straightforward equation can describe the cosmological coupling. Here, m is the mass of the black hole, and a is the scale factor that characterizes the universe's expansion. So I is the initial universe scale factor when coupling begins, and m of I is the initial black hole mass. As the universe expands to a scale factor of a, its mass will transform to m of a, so k represents the dependence of the ultimate mass on the universe's expansion. The term for this is cosmological coupling strength. According to their hypothesis, if there is no cosmological coupling in the universe, K is 0, and the initial and final masses of a black hole are the same as the universe develops, then there is no cosmological coupling. However, if cosmological coupling exists, K should equal 3, so the black hole's mass after the universe's expansion is greater than its initial mass. This is the essence of the intriguing concept underlying their investigation. The possibility that black holes could be a source of dark energy is intriguing, but is there any evidence to support this theory? How could they corroborate this theory when the interior of a black hole is unknown? To answer this question, researchers turned to low redshift elliptical galaxies where they had previously observed an increase in the mass of the supermassive black hole. Using the cosmological coupling equation, which defines the relationship between the expansion rate of the universe and the vacuum energy density, they compared the masses of these black holes with those of young elliptical galaxies. K, representing the coupling parameter, was unexpectedly determined to be 3.11. The probability of these galaxies having a K value of 0 was close to 0, showing that the black holes in these galaxies are cosmologically coupled with the universe. Additional analysis revealed that black holes could account for approximately 68% of the universe's total dark energy. This result also explains the coincidence problem, which asks why dark energy has lately dominated the universe. This study suggests that a complete evolution of galaxies is required for black holes to contribute to and dominate dark energy, speeding up the universe's expansion. As exciting as the proposed concept may sound, it must be acknowledged that it has some limitations. These result from several gaps in the hypothesis. First, because of the impossibility of studying a single galaxy throughout its existence, the researchers compared galaxies from different periods of the universe. However, this comparison implies that galaxies' evolution and growth paths were similar across eras, which may be different. Second, they assume black holes exert negative pressure, a property of dark energy. Third, the study only considers singularity-free black holes, which are not well established in the scientific literature. However, we cannot outright reject theoretical concepts such as this one. Some of the most revolutionary discoveries in physics and astronomy began as theoretical hypotheses. For example, the 1930 prediction of neutrinos by Wolfgang Pauli led to their discovery in 1956. Similarly, the discoveries of Neptune, the Higgs boson, and gravitational waves were based on theoretical predictions. Therefore, we must remain speculative and seek evidence to determine whether the concept is merely a mathematical beauty or if it represents physical reality. The Little Galaxy's Enigma. The mystery of dark matter is one of cosmology and astrophysics' most intriguing unresolved problems. According to astronomers, approximately 1/4 of the observable universe comprises of dark matter. According to estimates, 85% of the matter in galaxies comprises dark matter. According to our current models, the fundamental components of cosmological structures are dark matter halos. Consequently, they play an important role in the formation and evolution of galaxies, shielding them from the gravitational influence of their companions. With them, galaxy formation is possible. However, astronomers have discovered something peculiar in a galaxy cluster 62 million light-years away. Recent research on dark matter may pave the way for an entirely new branch of physics. So what makes the galaxies in this distant cluster so special? What challenges do these galaxies pose to our current cosmological models? How, most critically, will this discovery affect the future of cosmology and astrophysics? Dark matter is a hypothetical matter thought to exist nearly everywhere in the observable universe. Dark matter, unlike normal matter, does not interact with electromagnetic forces. As a result, it cannot absorb, reflect, or emit light, making it exceedingly difficult to detect. Therefore, it has been given the name dark. However, astronomers have presumed its existence because the star's motion and galaxy's dynamics would make no sense without it. Furthermore, according to various theories, the preponderance of dark matter is non-baryonic. This implies that the standard model of physics does not include subatomic particles. Instead, these enigmatic particles can interact with massive particles weakly or gravitationally. Dim brown dwarfs, white dwarfs, and neutron stars. are additional likely candidates, although even the most sensitive detectors could not discover conclusive proof of the existence of dark matter. The gravitational influence of dark matter on the surrounding visible matter shows that something mysterious, such as dark matter, exists. The issue is caused by dark matter. Halos. A dark matter halo comprises gravitationally bound masses of dark matter. Consequently, they impose a strong gravitational pull on nearby galaxies. However, if we cannot observe these halos, how do we know that they interact with galaxies? To comprehend this, let's contemplate a simple illustration. When an object exerts its gravitational force differentially on various parts of another body, it can distort that body's natural shape, causing tides. Because of the Moon's gravitational pull, it's analogous to Earth's tides. As a result, the Moon exerts a greater force on the side of the Earth, confronting it. It is believed that the universe contains trillions of dwarf galaxies. They are the most common and tiniest galaxies in the universe. Dwarf galaxies are typically found in massive galaxy clusters, or close to much larger counterparts. This renders these small galaxies susceptible to gravitational distortions induced by their enormous companions. However, their dark matter halos save the day. They partially shield the dwarfs from the massive cluster's tides, limiting their distortion. All galaxies are believed to reside at the center of a vast sphere of dark matter, which dwarf galaxies containing even higher proportions of dark matter than large spirals. This is because the sum of their stellar masses cannot completely explain the motions of their stars. An example is Tucana II, a dwarf galaxy of ancient stars near the Milky Way. It is devoid of ongoing star formation and has abundant dark matter. Halo, however, the Fornax cluster, located 62 million light-years away, is an exception. According to the standard model of cosmology, it comprises several warped and perturbed dwarf galaxies. If these dwarfs are surrounded by halos of dark matter, such distortions should not exist. The researchers analyzed the Fornax Deep Survey (FDS) data in their article. It contains information on 564 galaxies and is the most recent survey of the Fornax cluster. First, the researchers eliminated the galaxies they believed did not belong to the cluster and represented line-of-sight contamination instead. Additionally, they eliminated galaxies with ambiguous tidal morphology to improve the analysis. From the Fornax survey, they were left with 353 dwarf galaxies. To gain a comprehensive understanding of the peculiar characteristics of Fornax dwarfs, researchers attempted to comprehend the gravitational distortions of these galaxies and their causes. Each galaxy's distortion is determined by several factors, including its intrinsic properties and distance from the cluster's core, where gravitational forces are significantly stronger. Therefore, galaxies with large sizes but few stars, and those closer to the cluster's core, are readily perturbed. Researchers contrasted their cluster observations with the European Southern Observatory's VLT survey telescope, and their findings show some issues with the standard model. According to the conventional model, the dark matter halos of these dwarfs should partially protect them from the cluster's tides. In contrast, they are distorted and entirely unprotected. The galaxies in the paper were categorized as undisturbed, mildly perturbed, severely disturbed, and unclear. In addition, the researchers provided images of 3 survey dwarfs displaying varying disturbance levels in various color bands and filters. This picture depicts an undisturbed galaxy. This galaxy exhibits signs of tidal distortions, which places it in the category of being mildly perturbed. This is the image of one galaxy in the category of being extremely perturbed. Because of the gravitational influence of neighboring galaxies, traces of tidal perturbations can be observed. Suppose that the standard model must explain the observations. In that case, the Fornax dwarfs ought to have been annihilated by the gravity of the cluster core, even when their tides are 64 times weaker than their gravity. This contradicts previous studies in which it was found that the force required to disturb a diminutive is greater than previously estimated. The galaxy is roughly equivalent to its own gravitation. If the astronomers' findings are confirmed, then the standard model of cosmology requires significant revisions. Do we have any other explanation for the peculiar behavior of the Fornax dwarf galaxies? At least one alternative explanation exists for the peculiar galaxy morphologies predicted by the changed Newtonian dynamics model, also known as the Mond model. To account for the observed properties of galaxies, this model suggests that Newton's law of universal gravitation should be changed. Then it could explain the bizarre galactic appearances. In 1983, Israeli physicist Mordecai Milgram first proposed the concept of Mond. The original purpose of the hypothesis was to explain why observed star and galaxy velocities were greater than predicted by Newtonian mechanics. Therefore, it is an alternative to the dark matter hypothesis for explaining why galaxies appear to violate currently understood physical laws. While Mond is an ideal alternative to the lambda CDM model for describing the dynamics of spiral galaxies, it could be faultless. For instance, Mond cannot describe galaxy cluster masses by a factor of 2 to 3. In addition, it cannot account for the observations of the Bullet cluster located 3.7 billion light-years away. It will be fascinating to see which of these two models ultimately prevails. If scientists continue to discover more galaxies devoid of dark matter halos, we may need to reevaluate our current standard model of cosmology. According to our galaxy evolution models, even the James Webb Space Telescope has discovered candidates that should not exist for galaxies. This is an exciting period for astronomy. One of them is the candidate for Schrödinger's galaxy, which we discussed in the 20th episode of the series when Webb was operating at full capacity. Astronomers hope to discover dozens of candidates with a high redshift and thoroughly study their composition. Pole shift is happening. The Earth's magnetic field is one of its most important protective barriers. This invisible structure surrounding and penetrating our blue home planet protects it from the solar wind's charged particles. If the Earth's magnetic field did not exist, terrestrial life would not have developed to its current state. Would the magnetic shield be affected if the Earth's magnetic field changed significantly? Several such pole climbs have already occurred in the past. Our planet's magnetic poles are reversing. But how would this impact everyone? What else? Consequently, a procedure may have been started. Today's aim is to discover answers. On Earth, a magnetic field exists. According to various hypotheses, magnetic fields are generated by diverse methods. However, the dynamo theory is the most widely acknowledged. Likewise, it is believed that the GO dynamo is the mechanism responsible for the Earth's magnetic field. Based on the premise that the interior of the Earth contains vast quantities of electrically conducting liquid, this theory proposes that the outer liquid portion of the Earth's core completely encircles the solid center and contains a very high iron content, almost entirely composed of pure iron. It is estimated that the innermost regions of our planet have temperatures exceeding 9,000 degrees Fahrenheit. This value corresponds to the Sun's surface, nickel and iron's searing heat. Under the pressure and temperature conditions that exist in the Earth's interior, however, it cannot be magnetized. Therefore, they are solely conductors of electricity. In addition, the dynamo theory proposes that connections in the Earth's interior move matter. These currents transport molten material from the planet's interior to the cooler outer regions. After the material has cooled, it descends back into warmer regions. The Coriolis force influences the convection currents within the interior of the planet. Because of the planet's rotation, currents are deflected and directed along helical paths. According to dynamo theory, this helical motion sustains the present generation. Consequently, the initial, fragile magnetic field gained increasing strength. The magnetic field eventually became relatively stable when a limiting effect occurred. A defensive shield and a marker, the Earth's magnetic field protects us from the solar wind. This accounts for approximately 95% of our natural defenses. Electric currents in the ionosphere and magnetosphere contribute to the remaining components. A spatially variable interference field completes the magnetic field of the Earth. This procedure results in the appearance of breathtaking auroras. When charged, energetic particles interact with the Earth's magnetic field. Dazzling luminous phenomena occur. In addition, our invisible companion performs several other crucial functions. Consistent with its name, some animals, including pollinators, sharks, salmon, and migratory birds, possess magnetic senses. Because of the Earth's magnetic field, these organisms can navigate without error. Humans have used and continue to use the Earth's magnetic field for purposes other than navigation. The Earth's magnetic field is also suspected of directly influencing global temperature variations. Some experts are skeptical that manufactured climate change explains the accelerated warming of our planet. Consider a classic compass for a moment. In some experiments, cosmic rays have been attributed to cloud formation. In a biased poll, however, many researchers believe this link is insufficient to substantially affect global climate change. Upon examining the history of the Earth's magnetic field, we realize it is not a rigid, immutable entity, but a construct that undergoes dynamic change during its examination. The polarity of the Earth's magnetic field has reversed over thousands of years. How can these changes, sometimes traced back hundreds of thousands of years, be demonstrated? Magnetic fields cause magnetic minerals that are cooling to become magnetized. Scientists use the magnetization traces left in rocks when the temperature declines below the Curie temperature. Furthermore, detritus can be magnetized. However, ceramics are no different. Because of the magnetization of the oceanic crust, the principal magnetic field of the Earth remains essentially stable over extended periods, but its intensity fluctuates slightly. Therefore, the associated materials genuinely understand the natural processes that once occurred on our blue home planet. For this reason, their value in geology and archaeology is immeasurable. A pole leap in the Earth's magnetic field is also relatively common. Approximately every 250,000 years, the polar regions reverse positions. About 780,000 years have passed since the last pole leap, and this procedure is referred to by experts as the Bruns-Matsuyama reversal. The pole leap required less than 100 years. Unlike complete magnetic field reversals, temporary dips occur when the field regains its original direction. Unexpected developments. The magnetic poles could slowly adjust, but what would happen to them? They are already doing it because of the daily north-northwestward movement of the Arctic magnetic pole. The magnetic pole, therefore, moves approximately 19 miles per year. Besides its direction, the Earth's magnetic field can also be measured by its speed and intensity. These fundamental attributes are subject to continuous change. Gauss was the first person in the first half of the 19th century to measure the Earth's magnetic field. In 1839, the Magnetic Association concluded that the central position of the Earth's magnetic field derives from the planet's interior. Since our magnetic field was first measured a century ago, its intensity has decreased by nearly 10%. The intensity of the terrestrial magnetic field decreased by 6%. Observations by the swarm satellites show that the magnetic field intensity of the South Atlantic is diminishing. However, it is gathering strength in the Indian Ocean. Is there a rationale for this change's rapid occurrence? This interesting question still needs to be satisfactorily answered by science. The cosmological field intensity is decreasing. However, it is gathering strength in the Indian Ocean. Is there a rationale for this change's rapid occurrence? This intriguing query has yet to be satisfactorily answered by science. The magnetic field in the core is already altering its regional polarity and producing a forgery. Therefore, the global field could degenerate much more rapidly than would be permitted by passive decay. However, even if the dynamo failed, the magnetic field would still take 10,000 years to decay. Therefore, it is necessary to review two truths. First, statistics show that the polarity of the Earth's magnetic field reverses every 250,000 years. However, 780,000 years have transpired since the previous pole jump. The time for a new pole reversal has arrived. How would our lives change if the magnetic poles were tilted in this direction? The computer models of experts portray a stunning picture. Initially, there would be 4, 8, or more magnetic polarities. There would be no magnetic field on Earth in the traditional sense. As a result, our planet's protective shield becomes disorderly and chaotic. However, such events will not eradicate the invisible construct entirely. In the past, 10% of its current intensity existed. Therefore, terrestrial life is unlikely to sustain enduring damage. In such a scenario, Earth would be bombarded with more cosmic particles. Additionally, this would increase the prevalence of genetic disorders and malignancies. However, the Earth's magnetic field's polarity has never been explicitly linked to mass extinction. Homo erectus, our remote ancestor, survived the Bruins-Matsuyama reversal 780,000 years ago. How about the creatures that navigate using the Earth's magnetic field? According to several researchers, migratory birds and similar species are exceptionally adaptable. These animals realign their magnetic sense nearly every day. The animals oriented themselves primarily towards the sun at night, but their sense of smell, ocean currents, and geographical landmarks prevented them from becoming disoriented. In contrast, our technical systems are more susceptible to attack. For instance, passaging charged particles can occasionally completely obliterate electronic components. Specifically, the internet, television, telephone, and GPS navigation satellites would be affected. In addition, some scientists assert that severe magnetic disturbances could paralyze the U.S. power grid. As a result, such an occurrence would have many negative repercussions, such as a breakdown of water supplies, food processing, products, transportation, and the internet. Does this imply that the magnetic field of the Earth has already reversed? We must determine the answer to this query. The potency of our natural shield will be determined. The Parker Solar Probe departed our Azure home planet on August 12, 2018. Since then, NASA's spacecraft has conducted extensive research on the Sun. The outer atmosphere of our parent star, the corona, will be primarily focused on the mission of the uncrewed spacecraft. Io, the Moon. Io is one of the many peculiar objects in our solar system. The innermost of Jupiter's large moons is distinguished by volcanoes, the aurora, and sulfurous atmospheres. It has a specific context, so let's learn more about it. We currently know that Jupiter has 79 moons. A few orbits in and around the planet's rings are near the planet. In 1610, Galileo also discovered 4 massive moons, which he dubbed the Galilean moons. Io, Europa, Ganymede, and Callisto are listed from innermost to outermost. There are also irregular moons of Jupiter that are significantly more distant than the preceding moons. Io is only 350,000 kilometers from Jupiter's cloud peaks. From the surface of Jupiter, it would appear 39 times more conspicuous in the sky than our moon. Io orbits Jupiter in 42.5 hours, whereas our moon takes 30 days. The orbits of 2 of the Galilean moons align with their own. Europa orbits twice for every orbit of Europa, while Ganymede orbits 4 times for every orbit of Europa. This is known as orbital resonance. Orbital resonances increase the mutual gravitational influence between the moons, causing Io's orbit to be slightly more eccentric than without them. In its orbit, Jupiter's gravitational influence causes tidal heating, the primary heat source for most of its geological activity. On Io, tide bulges can reach 100 meters in height. Similarly, the moon causes ocean tides on Earth. Typically, Earth's tides are only 2 meters high or low, which is a much smaller effect. Because of its proximity to the massive planet in our solar system, I always experience 300% greater tides than our moon. Jupiter and the other large moons in the system prevent the moon's orbit from becoming less eccentric, so Io won't be able to relax for a while. In Io, a day corresponds to its orbital rotation. Therefore, it is tidally bound to Jupiter. Just as we can only observe one moon phase from Earth, from Jupiter, there is only one perspective of Io, despite its bulk. This Galilean moon is relatively large. Comparable to the terrestrial planets, our moon, due to its size and density being comparable to the moon, its gravity is also comparable. It has the greatest density of any moon in the solar system, which is an intriguing fact. This is one of its many distinctive features. In addition, it consists primarily of silicate, granite, and iron. Io is the smallest liquid entity in the solar system. Most of the solar system's other large moons are composed of water, ice, and silicates. An iron or iron sulfide core will likely surround a silicate-rich mantle and crust. Since no magnetosphere surrounds the moon, the core cannot be convective. A liquid mantle near the crust has a minimum thickness of 50 kilometers. Its surface is covered by a multitude of enormous volcanoes. Here is the origin of all volcanism. This is where Io excels. Before the 1970s, we knew little about the Internet of Things, Io. While observatories indicated the moon lacked water and could be covered with sulfur, Pioneer 11 was the first mission to investigate Io in depth, even though the quality required refinement. However, Io is composed of silicate rock instead of water ice, and its atmosphere is sparse because Jupiter's radiation interfered with the onboard command system of Pioneer 10. Close-up images of Io were not captured. Due to Pioneer 10's exposure to radiation, the maximum radiation around the planet was 10,000 times stronger than what Pioneer 10 experienced. In 1979, the initial and second Voyager missions to Jupiter were launched, with only 20,000 kilometers separating them. Voyager 1 captured close-up images of Io's surface. The landscape was completely devoid of impact craters and was filled with vibrant colors. We have mountains taller than Mount Everest and volcanic craters hundreds of kilometers across. There were also visible lava flows. However, it was notable that vapors were rising from the surface. There is no other location like Io, proving its volcanic activity. Beyond Earth, the phenomenon has been observed excluding cryovolcanoes. The study discovered that sulfur compounds dominate the atmosphere. Moreover, Voyager 1 confirmed that Io's surface is covered in sulfur thrusts. This is the reason Io is so vibrant. In March of 1979, Voyager 1 observed 7 of the 9 plumes, while Voyager 482 observed 7 from 1 million kilometers away. Therefore, it is probable that these volcanoes were active throughout those 4 months. The Galileo spacecraft arrived on Jupiter in 1995 and captured captivating images. Even though the spacecraft was not intended to investigate Io, it captured some of its best images to date. Because of mechanical malfunctions, Galileo could not operate at full capacity, meaning we would have obtained even better images if it had been entirely functional. However, volcanic emissions were observed. Volcanic eruptions were also confirmed. Magmas that contain sulfur and silicate similar to Earth's magma. Io's magma is also magnesium-rich. Io's surface contains an astonishing quantity of color. Yellow plains are predominantly composed of sulfur. Fresh sulfur dioxide frosts cover the vast majority of the polar regions. Because of radiation damage, the polar regions are more crimson than the rest of the planet. Red deposits left by volcanic emissions that reached hundreds of kilometers above Io can also be observed in other locations. Peel, a dormant volcano, has the most noticeable deposit. Galileo was also present. When Voyager passed, an enormous plume was visible. The plume is 300 kilometers in height and 1,200 kilometers in breadth, approximately the extent of Alaska. Intriguingly, lava flows typically originate in depressions at the summits of volcanoes. On Io, there are no depressions on lofty peaks. As a result, there are these lava lakes surrounded by tall walls. Loki, one of the most prominent volcanic depressions on Io, is displayed here. The circle's diameter is 200 kilometers. The legs are directly connected to the magma reservoir below, typically covered with a thin crust layer. Loki generates 25% of the average heat output of Io, but when the crust on the lava lake descends back into the lake, Loki's heat output increases by a factor of 10. A second massive volcano on Io shows this exceptionally well. Vashti is included as well. This area is typically white, but only white in this image because of the crust collapsing. Because of this intense radiant energy emitted by the magma curtain, the camera captured only white images. In 2007, Jupiter provided new horizons with a gravity assist on its journey to Pluto. Besides testing its apparatus, the company seized the opportunity. Vesta's lens focused on Io as it flew by, revealing details unique to Vesta. A cloud could be seen hundreds of kilometers above the surface of Io, emanating from the volcano I mentioned. Also visible around the moon are additional minor eruptions. This is the most remarkable spacecraft I've ever seen. Volcanoes are typically flat, but the highest mountain is 18 kilometers tall. Occasionally, mountain ranges and ridges connect these mountains, although the majority are not volcanoes. Lava lakes surround these mountains, signifying faults in the crust. Jupiter's magnetic field is another distinctive feature of Io. Jupiter has a vast and potent magnetic field, and Io orbits within some of its most significant sections. Particles are lost to space from Io's thin atmosphere, and emissions float in a natural cloud surrounding Jupiter. This cloud can stretch for many miles beyond and behind Io's orbit. Similarly, Jupiter's magnetic field generates a plasma torus, a donut of ionized particles. Io's orbit rotates at 17 kilometers per second, whereas Taurus's is at 70 kilometers per second. As a result, Taurus-originated particles bombard the neutral cloud during Io's orbit, causing it to gain energy. Attracted by the magnetosphere's magnetic field lines, these newly ionized particles enter Taurus. Approximately 1 ton of matter is lost from the neutral cloud each second into the Taurus plasma, substantially increasing Jupiter's magnetic field. If Jupiter's magnetosphere were visible, it would have a dimension comparable to the Moon's. However, there is more to the relationship between Io and Jupiter than meets the eye. The Io flux conduit is an electric current that connects Io's atmosphere and neutral cloud to Jupiter's polar upper atmosphere via the magnetic field lines that Io traverses. Flux tubes are essentially magnetic field line concentrations. These are visible on the Sun between sunspots because of the charged plasma that flows between sunspots. Io's flux conduit generates an aurora around Jupiter's polar regions. The flux conduit of Io collides with Jupiter's upper atmosphere. Aurora can also be seen on EIR. The colors that depict ionized particles are not limited to the polar regions. Sodium is green. The red hue is derived from oxygen, while the blue hue is derived from sulfur. Here you will find all of the information you need about Io. Pluto. Pluto has always been a source of controversy in astronomy. Does it make up a planet? Because of its great distance from Earth, Pluto was shrouded in mystery, and we knew little about its appearance. However, traveling through space took 9 years. The New Horizons mission of NASA was the first to reach Pluto. Stunning images of Pluto and its surrounding Kuiper belt have irrevocably altered our perception of the planet. Pluto and its extraordinary satellites, a magnificent universe before the invention of modern observatories, Pluto was considered the 9th and most distant planet from the Sun. Then, in 1905, an American astronomer named Percival Lowell discovered Pluto's existence by observing some peculiar deviations in the orbits of Neptune and Uranus, Pluto's nearest neighbors. According to him, the two planets may be pulled apart by the gravity of another world. Unfortunately, he passed away before its discovery in 1915, so he could not witness it. Clyde Tombaugh discovered the planet in 1930 at the Lowell Observatory in Flagstaff, Arizona, following the predictions of Lowell and other astronomers. Pluto's name also includes the initials of Percival Lowell as a tribute to him. Following the suggestion of 11-year-old Venetia Burney of Oxford, England, the Roman deity of the underworld was given this name. Scientists and astronomers have attempted unsuccessfully for years to glimpse the planet. Following the discovery of Pluto, there were many hypotheses and predictions, but no supporting data or images. The new world was too distant for precise observation, so NASA launched a mission to get up close and personal. The $700 million mission, to be exact. On January 19, 2006, Cape Canaveral launched the New Horizons mission to investigate the neighboring planets. Jupiter and Saturn were the primary targets for the New Horizons spacecraft, but Pluto was the ultimate aim. Despite the many obstacles encountered along the way, the journey required effort. New Horizons effectively explored Jupiter and its Jovian moons, returning many heavenly images and data that improved our understanding of the giant planet. The New Horizons mission gathered crucial data after its close encounters with Jupiter, Io, Europa, and Ganymede. After several course corrections and periods of hibernation, New Horizons was directed towards the Kuiper belt. The spacecraft required 9 years to reach its destination. On July 14, 2015, the New Horizons mission officially reached Pluto. It did a fast flyby of the planet, but could collect 6.45 gigabytes of data. Particle and dust detectors downloading the data may have taken a few minutes in the past, but it may take more than a few minutes today. Data transmission in space is distinct from data transfer on Earth because of the distance of 2.9 billion miles between the spacecraft and Earth. It took 16 months for the data to reach Earth. Throughout the spacecraft's exploration of the Kuiper belt, the third region of the solar system, it continued to move away from the planet. Here, Pluto once resided. This is where they made the discovery. Pluto was discovered to be a massive Kuiper belt object, or KBO, rather than one of our 9 planets. This enigmatic belt extends from 20 AU to 50 AU, circumnavigating the solar system. 1 AU is the distance between Earth and the Sun. Pluto is one of the largest ice objects in the Kuiper Belt. According to mission data, approximately 35,000 space objects are present in the region. This is not an ordinary space asteroid. It is the remnant of the solar system. By examining the formation of these ice rocks, we could gain a greater understanding of the solar system. New Horizons mission transmitted information about the belt. In the past, we'd only observed comets as floating icy bodies. Typically, comets are observed after the sun has warmed and transformed them. Despite Pluto's location at the border of the solar system, suspended in the Kuiper Belt, the mission allowed us to observe these objects in their natural environment. When Pluto was exposed to the cold, it was a busy and scientifically significant world. During its flybys of the planet, New Horizons captured every angle and image conceivable. Consequently, it was revealed that the planet possessed some remarkable characteristics. New horizons were observed, and high-resolution images were obtained during Pluto's flyby. The dwarf planet reoriented itself to face its moon because of the Sputnik Planitia region on its left. The mission transmitted images of a heart. The Tombach region is a vast 1 million square mile, heart-shaped nitrogen glacier. Charon, the largest glacier in the solar system, extends across the left lobe of Tombach for approximately 600 miles. Images and data show that the ice flow is largely crater-free and exceptionally juvenile. The detection of water ice on a distant planet was one of the mission's most exciting discoveries. Since water ice is limited, discovering additional water ice beneath the surface excited researchers. Existence is possible wherever there is water. There were also photographs of mountains as lofty as the Rockies. Because of this, and the absence of craters, the planet is geologically active. Other surprising Pluto features include dunes. The sand dunes on Earth are not identical to these. Granules of solid methane ice sculpt Pluto's dunes. It is essential to observe that dunes are uncommon in our solar system. They're found only on Earth, Mars, Venus, Saturn's moon Titan, and Comet 67P. LORI, the spacecraft's long-range reconnaissance imager, also captured a brilliant blue image of Pluto. The blue hue is produced by dispersing sunlight with hydrocarbon particles called tholins in the planet's atmosphere. You would be utterly mistaken if you believed the dwarf lived in a miserable, frigid world. In addition, the New Horizons mission revealed that Pluto is much more significant than previously believed. With a diameter of 1,473 miles, it can, once again, be considered a planet. In addition, the spacecraft gained stunning images of Pluto's moons. Charon, Pluto's moon, is a wild, wild realm. According to mission data, a liquid ocean may exist beneath the frozen crust of Chiron. In contrast, two other satellites in the solar system, Styx, Nix, Kerberos, and Hydra, rotated quickly while maintaining a face towards Pluto. Finally, a successful flyby of Pluto led New Horizons to encounter the mysterious Kuiper Belt object Erica Earth. This strange, lobe-shaped object is the consequence of combining two objects. Undoubtedly, it is the most primitive binary we have ever investigated. The images captured upon approach revealed its uncanny resemblance to an icy snowman. Nearly 4 billion miles from Earth, this object in the Kuiper Belt may contain crucial information about other primordial Kuiper Belt objects. According to the International Astronomical Union, the object's distinguishing characteristics are named after air, which signifies the sky, and Powhatan Algonquin. The team researching Kuiper Belt objects will assign names to Air Corps' most prominent features in 2019. The close-up image of the object reveals a nearly circular trajectory on the larger air lobe and a larger crater. Three characteristics receive unfamiliar names in the reduced first, as is, because it resembles a serpent. The arc will be named after the Mayan language of Yucatan. In Bengali, it is known as Quasar, which means sky. In English, the enormous crater is known as the sky. After New Horizons flyby, a few aircraft images were captured as it explored other objects in the belt. If another spacecraft cannot make the journey, we will never see Pluto or Earth again. Humanity has been compelled throughout history to seek the unknown and explore the world beyond. The Voyager spacecraft has shown that this force has no limits. We have already reached interstellar space thanks to two legendary sister spacecraft. No manufactured spacecraft, regardless of how impressive, can last forever. The New Horizons mission is expected to continue for another 16.5 years, traveling 311 million miles, or 500 million kilometers, per year, the distance between Earth and Jupiter. The crew suggests that one more space region can be investigated before time runs out. As with the Voyager probes, many scientists believe New Horizons may travel much further than expected. New Horizons are currently thriving and show no signs of slowing down. How will its future unfold? Time alone will provide the answer. There is still much to learn about Pluto and its satellites. Some consider it to be a dwarf planet in the Kuiper Belt. Pluto reigns supreme among the planets.